All right, so this is Relativity of Simultaneity and the Sagnac Effect, an ether cosmology presentation by your boy Space Audits. So we're going to be going over the principles of relativity and where they apply, and then we're going to look at the Sagnac Effect and see if relativity theory provides an adequate explanation for that measurement. So here we go. So before we begin, I'd like to start every presentation now with two concepts, kinematics and dynamics. If you remember nothing from this presentation, remember these two things. Kinematic means measurement. You'll see some equations here that govern kinematics. These are all describing change in distance over time based on velocity, right? This is how you find velocity. Equation number 3 here is missing a t squared at the end. It's a visual bug. Everything else is correct. But anyway, the point here, though, is kinematics means measurement without causal mechanism, right? Just predicting motion based off of previous patterns of motion, right? No factors for, no accounting for actual forces, right? And then dynamics would be actual predictions based on real forces, right? So kinematics and dynamics are two separate things. All right. And let's see, next slide. Okay, so here we have the speed of light derivation from Maxwell. We have 1 over the reciprocal of epsilon times epsilon times mu equals c. So what they're saying here is that the propagation rate in a vacuum is approximately 300 million meters a second. So they've got their metric for how they're defining distance propagation based off of electromagnetic induction, right? All right. So next up, we're told one of the many hurdles of history is that relativity theory was the only theory that could merge Maxwell's equation with Galilean dynamics. In other words, applying motion to Maxwell's equations. And we're told that through this, the story that we're told essentially is that special relativity with the introduction of the variable time in the XYZ coordinate system, that additional variable time allowed them to describe motion, because what is motion but change over time, right? All right, so Einstein has a particular flavor of how he defines time, though, in his theory. He defines proper time as the time in the moving frame, right? And then he defines the stationary frame as coordinate time. And the distinction he's trying to set up here is that, all motion is relative, and that in order to be existent, really, you have to be in motion relative to something. So what he's saying there by defining proper time is that the motion frame is the frame of importance, and the stationary frame, being coordinate time, is just some arbitrary, whatever frame, right? Is the way that he wants you to look at it. But Hertz came along and introduced time as an absolute, and then proper time, in other words, like the time in the moving frame, as coordinate time, right? So a differential from the absolute gives you the time for the motion frame, and everything is restored. Everything's fine. There's no issues. So that's one of the many stories that we're told, is that without the introduction of special relativity, one couldn't even begin to even use Maxwell's equations or whatever the kind of stuff they spin. But it's patently false, right? It's literally the same thing, but instead of two differentials, it's just one's an absolute, and then the other one's a differential of that, right? So just breaking a little piece off to figure out the difference. All right. Okay, next one. So some experiments leading up to relativity theory are Fizeau, Arago, Airy's failure, right? Experiments that were using light to detect the motion of the Earth, and some experiments using water or a moving media to measure the translational speed of that moving media relative to the speed of light, relative to that induction rate that was derived earlier, because this is going to give them this rate of induction here is going to give them the ability to make predictions of velocity based off of this number. All right, so come back now. All right, so these experiments were done, and they gave, what they say is a null result for providing evidence for the velocity of heliocentrism. And to rectify this, in 1905, after the Michelson-Morley experiment, which we'll come back to here in a second, but after 1887, that was like the final straw for experimental proofs of Earth's motion. They really didn't know what to do. There was, conclusive evidence of null results. So insert 1905 with the special theory of relativity, which says that as the consequence of the constancy of the speed of light, an observer in motion will observe events that are simultaneous, different from an observer who is stationary. So they'll make two different observations. Now, of course, we know that there's relative motion, relative Doppler shift, for example, right? But we know in reality, say, for example, if these two lightning strikes, if they strike at the same time, let's say they would send a signal to a bomb that would go off, right? Now, we know that if the lightning strikes at the same time, somehow, let's just say somehow you could time this so that they're synchronous. If they strike at the same time, that bomb is going to go off regardless of if that observer on the train is in motion, because he sees the signal on the B side first because he's moving towards it, right? Versus the stationary observer who would see them simultaneously. Well, there's no discrepancy in reality, right? We all know that the events happened, that the bomb would go off. So there should be no question of the principle of relativity of simultaneity, because this, just that example right there shows you that relativity and simultaneity are not two terms that can be added together to make a cohesive worldview. Because you can either be, if you're simultaneous, you're not relative, right? All right, so here we have a look at the Holy Scriptures from On the Electrodynamics on Moving Bodies from Albert Einstein. And here he's saying that, we attempted to discover the motion of the earth relative to the light medium, couldn't do it, can't be done, blah, blah, blah. So maybe there's no idea of absolute rest, which is where we're going to get into the idea of defining proper, like you'll see the logic behind defining proper time and proper distance frame, because, there's no such thing as rest. And if you're important, right, you're in the moving frame, so to speak, would be the kind of the way to look at it. So anyway, he suggests here that based off of Newton's equations, where they hold true in inertial frames, any frame that Newton's equations hold true, so will the special theory of relativity. And he goes on to say that so that's the first postulate, right? That all inertial frames are equally valid and that these equations will hold true in those frames. And then secondly, he postulates that the propagation rate of electromagnetic waves in a vacuum is constant at 300 million meters a second, roughly. And it's independent of the state of motion of the emitting body. And right here, it doesn't appear like he's saying anything new or anything, right? Because everyone knows that the speed of a wave is measured relative to its medium and the velocity of the observer, right? The motion of the observer. So what does he mean by this? Well, he means if you're in relative motion, right, with that emitting body, you're not going to be able to measure your velocity against there's going to be no change, right? Because it's a constant. So he's putting this forward, of course, to explain all these experiments that were done that gave a null result for the velocity of Earth. And then he goes on to say here, we don't need an introduction of a luminiferous ether. So this comment in particular is describing the physicality of the medium, right? So the ether wasn't just an abstract mathematical concept that provided a reference frame where they could use it to measure all motion relative to it. It was also postulated to be a material media that was necessary for electromagnetic propagation. And so he's saying here that not necessary, it'll hit up that vacuum speed. There's no need for an ether. And then he goes on to say that we don't need an absolutely stationary space to be provided with special properties where we'll assign velocity vectors for electromagnetic propagation in that empty space. So what he's saying there is that for bodies in motion, and when there's electromagnetic propagation going between them, if they're going at the same speed, right, if the motion is rectilinear and uniform, then because of the constancy of light, you won't be able to measure a velocity, and there'll be no discrepancy. And otherwise, you would be measuring velocity with respect to some point. And he's saying that's not what we're going to do here. So we're not going to be able to invoke absolute space for measurements with electromagnetic propagation, in short. Okay, so then he continues on here to lay out the kinematics of the theory. And I already talked about time earlier a little bit, but we'll just give a quick recap here. So he's saying that time is not an absolute, in the sense that if I said, meet me here at 7 o'clock, everyone in the entire world would instantaneously know what my 7 o'clock is. What he's saying is that this is like a local phenomenon between two people, in their relative motion state. So 7 o'clock, if he says meet me at 7 o'clock to a coworker, well, that guy's going to know what 7 o'clock is, right? Their relative systems are in the same spot, like they're aware of each other, right? So they're in the same time zone. But if he said it to somebody else, well, is it my 7 o'clock, your 7 o'clock? So that's what he's putting forward there, that there's no absoluteness to it. So you would always have to think of it through this lens of relative to some coordinate time, right? Just some arbitrariness, because there's no true rest. All right, 1 second. All right, so here he's laying out the rules for clock synchronization, and he's saying that based on the one-way speed of light here, how he's deriving this is that the time for the propagation that would go from T to B would be equal to the time of T prime A to B. So what he's saying there is that because there's a lot of like ambiguity in modern times that you'll be told you can't measure the one-way speed. We don't know the one-way speed. I mean, you can assume the one-way speed because it's, it would work out going that velocity going the one way and then the second way, blah, blah, blah. Well, let's just look at what Einstein specifically defined it as, right? It's going to be equal to the two-way, the one-way trip is going to be equal to the two-way trip. What could that imply, lads? Is it the same speed going back and forth? All right, cool. All right, so just another quick look at that those are going to be proportional. And then we have, let's see, on both sides, on the one way and the two way. So then we have on relative lengths and times. So here we were talking about absolute space and using that for electromagnetic processes. Well, here he's introducing motion to the clocks now, and they're not just two stationary clocks. These are two clocks in motion. And here he shows that there's a discrepancy with respect to absolute space. These clocks will not be in sync when you introduce motion. Now, he's going to tell us how much they're going to be out of sync by. So this is going to be his prediction for relativity theory, right? So this is going to be the introduction to the derivation for link contraction and time dilation. So we're told that so the postulates so far are that all inertial frames are equally valid. So these equations will hold true there. And that the speed of light in a vacuum is constant, irrespective of the motion of the emitter or observer. And then, but to mathematically, he shows that that's not true. But to get us back to those postulates where there's a constancy of C in this relationship, you're going to have to do a Lorentz transformation. And as a function of your velocity, as a function of the square of your velocity, you're going to experience physical link contraction and time dilation in your moving reference frame. And it's going in your then that contraction is going to be a function of the square of that velocity. So it's going to be a real tiny amount, right? But as you're moving at these relativistic speeds, it's going to increase, and as you decrease in speeds, it's going to decrease a ton, right? Because it's not a linear function, it's not proportional. It scales hyperbolically based on the velocity going up or down. Okay, so that's in a nutshell link contraction and time dilation, and then the relationship with velocity. So what he's saying here is that if the clock in motion at a speed nu is fast enough to invoke link contraction time dilation, then in that frame, it'll still be in sync, but it'll be off by just that little amount because of the contraction that the apparatus is experiencing due to the constancy of C, right? So a lot of people will say, well, is link contraction a physical mechanism? They're like, well, it's never been described. I don't know, like you blah, 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 right? Well, it has to be a physical mechanism if physical reality is a consequence of the constancy of C. There's no way to say that it's not the physical mechanism, at least in the reference frames that we're measuring it in, where we're supposed to be already contracted. You would have to absolutely argue that it is a physical mechanism. You would have no other way to look at it. It's pretty clear. You would have to just say you're already contracted, so you would never know. All right, and then we get into the physical meaning of the equations with respect to a moving clock. So we talked about clock synchronization and link contraction when you apply the correction for the square of the velocity. So he's going to show us here now where his equations apply and how much this clock is going to be desynchronized due to its motion. So he says, and if a clock at A is moved with a velocity nu along the line AB to B, then on its arrival at B, the two clocks were no longer synchronized. But if a clock moved at A to B lags behind with the other, which has remained by B by 2/2 times T nu squared over C, T being the time occupied by the journey from A to B, it is at once apparent that if the results hold good for the clock, if it moves from A to B in any polygonal line, and also when its points from A and B coincide, So any closed polygonal circuit, okay, looking good so far. And if we assume that the results proved for any polygonal line is also valid for a continuously curved line. And if anyone would like to give a quick shout out on what shape a continuously curved line makes. Quick shout out.
A circle.
Yes.
What?
Well, a circle, sure. All right. And then we'll go with circle. So thence we conclude that by bound. So anyway, he just wants to make clear here that he's not talking about, because they didn't have atomic clocks in his time. He's making sure here that we're not talking about a pendulum clock that's swinging back and forth, but he's talking about a light clock. So he's talking about, think about like a ping pong ball, in synchronization with another ping pong table, and they're just bouncing that little bead of light back and forth. That's what he's describing here, and he's saying that ping pong table B, when it completes its circuit, will be out of sync with clock B at this ratio, right? At 1/2 times t nu squared over c. All right. Then we have relativistic velocity addition corrections, just to make sure that the speed of light is never exceeded. We have a little reduction factor there to just make sure that we're always in the confines of relativity and never exceeding it. Unless Fresnel drag is involved, then we can do Galilean velocity addition because reasons. All right. Very cool. So we learned a lot about the framework and the math that's being applied here. But what a lot of people don't know is that the framework that Einstein uses adheres to something called Lorentz symmetry, which is part of a theory that was entirely based on a theory that was put forward by Hendrik Lorentz before 1905 for his theory. And he was using link contraction and time dilation as a physical mechanism with respect to a stationary ether that would physically contract and dilate time relative to the velocity of a moving body going through that stationary ether. And the cool thing about this framework is that when you do a summation of the transformations, you can get back to I call it the lab frame, but you can get back to that absolute space, right? So Einstein was talking about, so what he's doing is he's deleting absolute space from reality with the contraction, essentially, right? And then you could unwind it with a transformation back to the stationary rest frame. And you're like, oh, look, that's how much it would deviate from me if you were moving at this, blah, 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 right? And everyone's like, oh, cool, no way. Well, also, if you do a summation of that, it makes a complete, you could geometrically look at it as a triangle, and that would establish the motion to be with respect to an absolute space. That would enable you to unwind the mechanism of the link contraction and have it preserved with respect to absolute space. So in other words, this mathematical framework that's been thrust upon us through the lens of relativity that explicitly claims to not adhere to a framework that requires absolute stationary space to assign velocity vectors to, has it inherently built in every Lorentz transformation that's ever been done already includes this in it, and you can use it to establish things like absolute simultaneity and a cohesive line of events for clock synchronization, etc. So there, that's cool. All right. Any questions so far, lads? Any cues for the boys?
Tapioca Weasel asked, what does absolute mean in this context?
Absolute means absolute, man. Like exactly what it means. So in relativity, when they're like, oh, it has to be relative to somebody. Well, no, all motion is relative to absolute space and time, right? Because they literally use light to make measurements against it with interferometers and stuff, which we'll get into. So absolute means absolute.
Okay. So does that mean that there's a frame of reference which is the absolute frame of reference, and there are frames that are not?
What do you mean?
I mean, how would you identify the coordinates of absolute space? I guess is what I mean.
It's a good question. So the way that I kind of would look at it in this respect, right? When we get into the interferometry predictions, when they're doing V over C, you could say that they're using the propagation rate of C in its inertial frame. So they're making the measurement with respect to light's inertial frame, which would be like a conceptualization of absolute space. You could look at it in that way. That would be like a real easy mathematical way to do it for that. Does that make sense?
I'm not sure actually if the idea of an inertial frame for light does make sense actually, because light doesn't have inertia.
Well, it has a speed that it would be measured against, right? Plus or minus. So they've got their induction rate for C that's known as the constant. And then relative to the latitude, they make measurements where it's, plus or minus that. So,
Relative what latitude? Sorry.
oh, like, so you know how like Michelson, Gale, Pearson, 15 degrees per hour, that kind of stuff?
Okay.
So those measurements are made with respect to absolute space. Now they say in this, because it's rotation, right? They say that it's with respect to the rotation of the ball, of the spinning ball, right? But I'm just saying that the speed of light, it has a frame where that speed would be its speed, and then it would be propagating with respect to like its material media, right? So here on Earth, there would be an ether wind carrying it relative to its latitude. There would be a velocity difference relative to the lattie, and that's what they measure with interferometry, right? So
Okay.
C has its base speed, and then when it's in a material media, which was proven by Fazal, there's a drag.
Okay, so you're saying that but the idea of the ether is that you would also see evidence of some contribution to the drag that is not due to the material as it was in the Fazal experiment.
Yeah. So, for example, when the fringe shifts exceeded the refraction index, like in Sagnac with air, so the velocity fringe exceeds the prediction of like Fresnel drag for air being the mechanism, where the fringe would only be 44% of the velocity with respect to going with or against.
Oh,
And
okay.
then
I don't quite follow that because the refraction index of air is very close to 1, so I don't know where the number 44% would come in. But
yeah,
but
no, I got you. So taking it back to Fresnel drag, right? The hypothesis was that the ether was a material media, and that when it interacted with
it's a
another material
it's
media, it would be dragged.
question.
And the prediction was a ratio of 88%, 44% going with the velocity, or like going in the direction of the velocity of the material media, and then 44% going against it. So that's what they measured in that. So when I say the refractive index of air, there was a continued history where they were trying to, where they basically continued out the Fresnel experiments. So they used, instead of water, they used mirrors, or like crystals. And then they
So
were like, oh, hold on one sec. And then Sagnac came along and was like, oh, will this work in air? Right. And the fringe shift pattern, like that distance created from that velocity exceeds what would be measured if it was the air carrying it through like a refractive index at that ratio of 44%. Does that make sense now?
well, the specific number 44% doesn't, but I don't actually. That would be an unreasonable expectation because generally, when you get numbers, like 44%, there's a fair amount of very specific argumentation behind it, which I do not expect you to provide in a few sentences.
Yeah. So it
I
was so
I do have one clarifying question that I think will be helpful. Um, when you say Fresnel drag, is that basically the same thing that was measured in the like Fitsu drag, like when you have a
yes, yeah,
moving media?
yes.
Okay,
Yep.
okay,
Yeah.
okay.
It's called
I
Fresnel drag, but it was done by him. Sorry. Yeah, I got some slides later on for that. But yeah, so that's my basis for jumping up. Like when I say light has its own inertial frame, right? So it would have its own speed, which is measured at 1/square of epsilon mu, right? So, and then because the ether being a material media that's in motion in our realm, right? There's going to be latitude dependent variation. So it's going to be catching a velocity boost or velocity subtraction going against it relative to the lattie, because vortex, right?
uh, I mean I wouldn't have used the word vortex. I was up with you until you said the word vortex, but yeah.
Well, I can show you some stuff, but that's kind of that's what I'm talking about when I.
I don't want to derail the whole conversation. There are a
No,
lot
no,
more
you
people than me in the room.
no, no, you're good. It's super relevant though, so like you're doing great. It's like what we just touched on is actually covered as we continue. So maybe as I go through with the slides and stuff, and you see some of the experiments, it'll start to marinate a little better. But no, you're totally fine, bro.
All right,
You're
thanks,
you're
Alan.
you're absolutely on point. All right, so lab frame. And then, okay, so Michelson-Morley here. So we got the data set, and this is an analysis done by Consali. Can't remember his last name. Or that is his last name. Can't remember his first name. But anyway, he goes over the Michelson-Morley data. So we have 6 days here where they redefined all the physics over these measurements for the null results. And they say that, there was no fringe shift pattern significant, blah, 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 because the prediction was for 30 kilometers a second. So they expected 0.5 of a fringe or 0.005 of a fringe. And they ended up measuring just over one fringe. I think it was like 0.012 or something like that. But anyway, what this dude does is he does his own analysis of the measurements. He does a harmonic analysis. So what he's doing here is breaking it down, like doing some statistical variation analysis that involves sine waves. So we'll look at those here in a second, and we'll see what his conclusion was. So we're often left in the dark about the error tolerances and accuracy of the Michelson-Morley experiment. But we have Max Born, who went on record here quoting saying that the error tolerances are plus or minus 0.004 of a fringe. So that's pretty cool that we have an actual number here to put to a name to the face, as they say. All right, so now we're going to look at the harmonic analysis by your boy. So what we're looking for here is the sine wave to intersect with the error bars. And we've got some nice intersections here for the measurements. So what this means here is that you can say with statistical confidence, have you ever heard someone say, oh, with sigma 5 confidence, with sigma 3, et cetera, that kind of stuff, it comes out of statistical analysis. So what he's putting forward here are measurements that are non-zero measurements with statistical confidence that, he uses sigma 3 and sigma 5 for a couple of the different ones. But point being here is that these aren't null readings. These aren't, they're over the expected amount, but they're not what they expected for heliocentrism. I'm sorry, they're over the error margin, but they're not what they expected for heliocentrism. So the rounding it down to 0 and saying that, oh, we can't measure it because relative motion, link contraction, et cetera, was the jumping off point for the solution to this when they clearly made a statistically significant measurement. So here's another look at what that data looks like.
What does heliocentrism suppose should have happened that it didn't match with?
Heliocentrism supposes that they should get a fringe that would correspond to 30 kilometers a second. So a much bigger gap in the fringe rating.
Heliocentrism or no, wait, hold on. Never mind. Ignore what I just said.
You're straight. So this is just what the look like here. So this is what that data is plotted. So just, you can see it nice and clean. All right. And then we have another form of the data graphed out here. So all within statistical significance, but just not what the heliocentric model would require. And then here we have another, we're going to move on to Michelson, Gale Pearson here. So this is a analysis that the same gentleman did of 10,000 runs of day 1 of Michelson, Gale Pearson. And this is just an analysis on the min-max of the amplitude of the fringes. So just kind of seeing like, was this noise that was measured, or were these min-maximum dimensions that they're plotting against sidereal time to get their verification of rotation? Are they meaningful? And as you can see here, looking pretty sharp from the graph, right? All our min-max fringes are in the required area for statistical significance, as they say. Now we're a quick look at the Lorentz transformation equation. Here, it actually predates even Lorentz's use of it for his ether theory, where he was going to use it for contraction as the mechanism. Well, this dude, Woldmore Voigt, was using it for relative Doppler shift. He uses the Q function here slightly differently, so that contraction mechanism, he multiplies by it instead of dividing. So, but if you divide or whatever, it gives you the link contraction, like in the relativistic sense, and then the other one is what would it be? Transverse and longitudinal. So one gives you the longitudinal Doppler shift, and the other one gives you the transverse. So this framework was already established prior to Lorentz and prior to Einstein, and it wasn't being used for removing the media and saying that reality is contracting. It was just used to describe Doppler shift, relative Doppler shift. All right, so we got some. I think this is supposed to be earlier in the prez. But yeah, so we got some experimental verification for light. So when people are like, well, how do you know that Maxwell's derivation of 1 over the square of epsilon nu is or mu is correct and whatnot? Well, Fazal also did an experiment using a cogwheel rotating at a fixed rate that would flash after it hit a mirror. So he's just basically measuring how many flashes he would get over time with respect to the rotation of that cogwheel. And through timing that out, he got pretty close to the speed of light. I forget what the exact figures were, but that was like the first big one that they were that they used. And then, of course, the Fazal, dang it, kicked me all the way back. Hold on 1 second. This new setup's a little sensitive. Okay, cool. So they had their so they're getting close to approximating C here, and then with their predictions and everything, they do the Fresnel drag test, right? So in here, they've measured C, and then now they're using it to start to measure translational velocity. So here in this configuration, they have moving water going through a tube, and they have a split beam that's going to go with and against the water, and it's going to recombine and create a fringe pattern. So what they found was, and they were already using light and fringes to measure refractive indexes and stuff when they talk about the refractive index of stuff and all that. All of that is, basically done with a form of interferometry, essentially, right? Because the fringe patterns would correspond to the reduction in velocity for electromagnetic propagation going through it.
What year was this?
Let's see, 18. Let's see, 1 second. Pull it up.
Because the wave model of light wasn't basically from the time of Newton until I think Young. It wasn't very popular. So I thought that you basically had to wait until Young with the double slit and whatnot before the wave theory came back, and I thought that was roughly 1830, but I don't actually know.
No, so Fazal confirming Fresnel drag 1851, and then Arago before that did an experiment.
That's a super cool experiment. Oh my god, that is so cool. The Arago dot.
Yeah. Okay, so the Arago dot is what made people abandon the corpuscle theory, because the fact that it recombines like that would only happen if it was a wave. So that really tilted the balance for a lot of people.
It's this is just a very dramatic story in the history of science. So what happened was that Fresnel, I think it was Fresnel who was doing his dissertation defense basically for his doctorate in the early 1800s, and on his PhD committee were a number of eminent scientists, whatever, including notably Arago and also Poisson. And Poisson was a big deal because he was Poisson. And Poisson was
Shout out to
this is an
Poisson.
absurd hypothesis that light is a wave, because if it was a wave, then you would expect if it diffracts around a solid disk that you would have a bright spot in the middle. And Arago was also on the committee, and he was like, well, yeah, but have you actually done the experiment? And he did the experiment, and he found that there was in fact a light spot in the middle of the shadow of a solid disk. And it shows you that even the people that are most respected in the community, like Poisson, can just be wrong.
Yeah, dude, that's epic. I did not know the full extent on that. That's awesome.
Mm-hmm.
But yeah, they went with, that was pretty pivotal there. So yeah, the prediction here was, anyway, this shows the ratios that they use for the speed of light shows that they were on the right track, right? Because they're measuring the proportional velocity of the water. So like I said earlier, it was 88% going with, 88% going against. So 44%, 44% going with, 44 against, 88% total translational speed measured when you add them together. And they show that with the fringe displacement. So they're starting to hone in on measuring translation. They're starting to measure motion now, right? They're like, oh, this is, what else can we do with this? Where do we go from here? All right, so we have the next step, which I think was, let me follow the notes here. Second, so I can get the years right. All right, so we have Oliver Lodge in 1893. with his setup. So what we're looking up here is how he was setting up his interferometer for rotation, and this is his observation box. We'll see the total product of it here. So we have the motor and everything here, 2 spinning disc above to produce our friend shift, and I think he had cardboard or something to separate the big rotating disc. But what he was doing here was to see if the mass of the rotating disc would produce a friend shift pattern. In other words, he was looking for a friend shift based on mass, essentially, right? So this was like the first time they did that, and his results were pretty lackluster. Didn't really work out too well. There was a guy who did them recently on the YouTube channel, Planum88. Highly recommend that guy's YouTube channel. He does a lot of awesome experiments with interferometry and the history of light and all that. Very cool guy. Highly recommend. But anyway, his results were better than Oliver Lodge's, but not significant enough to be meaningful. So then this was done with modern tech and stuff, so more accurate and precise and whatnot. But to move on from that now, after Lodge's experiment, he was like, oh, well, we should keep doing it anyway and see if we can figure it out. But remember, we did have the successful measurement with Fresnel drag. And so carried on by Franz Harris in 1911 was a configuration where instead of using a running water, the media would be glass configured in a octagon around the interferometer, essentially, right? And what he did with that was measure, again, so where he measures the same ratio, 44%, basically Fresnel drag again, but this time for a device in uniform translatory rotation, right? All right, so we're going to look at the Sagnac apparatus here, because in 1913, Sagnac came around with his apparatus, and this was the first time that the friend shift pattern would exceed the friend shift that was predicted due to the velocity of being dragged through a medium. So, in other words, the refractive index of air isn't carrying around the light at the, it's at a proportional velocity of the rotation to create the effect. This is with respect to some other mechanism, right? So this is where you would have to explain this by saying that there was a path link change due to rotation. This is where you would have to start invoking absolute space, et cetera, to explain the measurements, because they exceed the causal mechanism of being dragged with the refractive index. All right, and then we'll come back to this orientation, or we'll come back to the Sagnac device specifically, because he did this, or this isn't the actual configuration that he used. He used a specific configuration, which we'll come back to the significance here in a minute. But let's just continue on here. So what they're putting forward, what was put forward in 1905 to explain these experiments that were trying to measure the velocity of Earth using light, they said, oh, well, you know what? The fixed point of origin, there's no absolute space for us to measure. So even though in their conceptualization of motion of the solar system, the Earth is going in a circle around the sun, they were like, oh, well, it's an ellipse now. And because it's so big and stretched out, it's actually a straight line. And because if you're moving in a straight line, you're basically in uniform transitory motion. And if you're in uniform transitory motion at relativistic speeds, you're going to experience link contraction and time dilation as a function of that. And so, that's why we can't measure that. So it's the removing of that absolute space. But here we're seeing it's going to have to be brought back for a rotating interferometer, because there's going to be no way to explain the timing difference in the phase going with and against the rotation. All right. So here we're going to look at, so we're told that these interferometers, or before we move on real quick, we're told that these interferometers, that the closed loop circuit measures a specific type of motion. It only measures rotation through angular displacement. So it can't measure like the translational velocity of it. It can only measure the angular displacement. So it can only be like 15 degrees per hour, 14 degrees, et cetera. It can't be like, we're moving at 8,576, or, you know what I mean? Something like that. So that's the way they look at it. And then they say that if the interferometer is configured where the light is moving at a right angle to itself, then that one is supposed to detect linear motion, and that one can't do it because Michelson-Morley. So instead of cohesively coming up with a theory that unifies the measurements, they divided the two apparatuses that are used to make the measurements, and that's how they do it. All right,
Wait,
and then
Hold on.
what's
hold
that?
on.
Yeah.
So you're saying that because you don't see a shift from Michelson Morley, so the argument, as I understood it, of the paper or experiment that you just presented, as I understood the argument, it was that there isn't a translational component to the fringe shift, because a translational component would have been precisely what the Michelson-Morley experiment was sensitive to, and it didn't see a consistent fringe shift with that hypothesis. So instead of it being a translational contribution to the fringe shift, it is a difference in the rotation rate. That doesn't seem like contradictory to me.
So they have them explicitly divided up to say that the right angle interferometer doesn't even measure the rotational displacement, right? Because that's what Miller measured. If you look at Michelson, Gale, Pearson, and you look at how they plot the periodicity and the min-max fringes, right, against sidereal time to get the sine waves that look all nice and cohesive, that is the same thing that Miller measured with the right angle interferometer. So they never actually measured, like there's no difference between linear and rotational motion, but because of the configuration of the apparatus, they've told everyone that this one measures linear velocity, but it can't be done because relativity. And the closed loop circuit measures rotation with respect to absolute space, because if you're in rotation, you're going to have some fixed point of origin for that, outward rotation to be relative to, right?
You're going to have a well-defined, axis, and in
Yeah.
that sense, it is absolute.
Yeah, for sure.
And
So,
I don't disagree with that.
yeah.
It's not generally what physicists, I think, mean by absolute, but I also think, and this is why my very first question was, what do you mean by absolute?
Oh, so
It's a
yeah,
difficult and a remarkably subtle thing to actually
gotcha.
precisely define.
So yeah, when they're talking about absolute space, right? It can't be the Earth for them because the Earth is in motion. So absolute space defined by the mainstream is with respect to the stars. So when they say that this, like a local Sagnac device in the lab is rotating, its rotation is with respect to the absolute stars. When they say that it's measuring, Earth rotation, yes. Thank you, the distant stars. So when they say they're measuring Earth rotation with the apparatus on the ground, they're saying that the rotation of the Earth with respect to those distant stars is where that absoluteness comes from. But I would just argue that it's the Earth frame. So
Okay. Yeah. I assume you're very, or at least somewhat familiar with Mach's principle. I find Mach's principle to be a fascinating way of
yeah,
approaching this topic.
I think he was half right. He said that the absoluteness was with respect to the Earth and the distant stars. So he half
Well,
nailed it.
that's one way of putting it. Another way of putting it is that Mach would say that there is no difference between you swinging a bucket around your head and and the universe just on its own swinging around your head,
Yeah,
which is a much less obvious way of putting the mathematically equivalent idea.
yeah. All right, cool. So before we move on here, or actually we're gonna move on from that slide.
Before you go, bro, I have a question.
Yeah. What up, SE?
What's up? We're going to let them get away with this distant stars being absolute non-motion. I mean, to me, that sounds like a contradiction right there. That kills everything.
Yeah, I mean, like I said, I would argue that the absolute space is the Earth frame, where all experiments have been done, where the laws of physics were derived, where everything has to be covariantly scaled to. So that's where I would argue it. But it's like a philosophical impasse. I'm not gonna not here to make him see it differently or anything.
Okay, I just wanted to point that out.
No worries. So here we got equations that describe motion of the acceleration in rectilinear or circular, right? So we're told, I'm going to show the configuration here so that it's more clear. But as I was going over earlier, we're told that one configuration measures a specific type of motion and the other interferometer configuration measures the other type. And somehow the universe makes a distinction between the two. So if you're moving in a straight line, the universe has its eyes closed to you, it can't see you, completely blind. You know, you're in Lord of the Rings and you're wearing the ring, nobody can see you, right? Or however it works, I forget. But anyway, but as we can see, the equations that describe them are all the same. There's no distinction. Like, how would you ever make a difference here? They're all describing the same thing. Like it's motion, right? There's not, if you look real close, you're not going to see a different kind. You'll see a different symbol here to indicate rotation, but you're not going to, like, where's the difference at? Okay, it's going to be a change in time when it's straight, change in time when it's rotate. Okay, they're the same.
Well, hold on. What's changing in time?
The position.
In velocity, yeah, in one of them it's the rectilinear position, and one of them is the angular position. Those aren't the same thing.
So in terms of using light to measure them, they are identical. And this is
They're
noted
not.
in well, they are, because it's explicitly how GPS works. It doesn't matter if you're traveling in a circle or if you're going in a straight line, you're going to receive the signal with a delay proportional to your velocity. And they don't account for it.
If you're assigning an angular velocity to light, you're not describing its motion through space. You're describing its oscillation in its poorly defined own frame, I suppose. You're describing the actual oscillation of the electromagnetic wave. You're not describing how fast that packet of energy is actually propagating through space. Those aren't the same thing.
Which one of these equations is not describing motion?
Motion is a very general concept. They are all describing motion.
And they're all describing it in the same way, right?
No.
Okay.
The first column, for example, you would use units of distance over time. The second column, you would use units of radians over time. Radians are not a distance. They do not have dimensions of length. They're a pure number.
Gotcha. But it's a displacement over time, right? Because that's really the key factor here. How you differentiate it and want to sector it out based on how you can analyze it mathematically isn't the same. Maybe perhaps I should have worded that differently, but what they're all describing is motion, and there's no distinction between motion, right? It doesn't matter.
The only way that they are the same is when you reduce it to the mathematics. If you actually look at the physical like what you're actually talking about, in one case you're talking about a distance between 2 points, and in the other case you're talking about the angle between two lines away from the center of a circle. Those aren't the same thing. Like, fundamentally, those aren't the same thing. You use the same mathematics to describe them because mathematics is a very versatile language.
Okay, let me rephrase then. So let's take an observer on the rim of a device versus an observer in linear motion. Now, the angular displacement with respect to the center of the device is going to make that triangle, like you were saying, right? And then the linear displacement is just going to be a straight line. But the important thing to note here is that they're both moving. There's both a change in over time. The universe isn't like, oh, he was moving in a straight line. This one was a circle. Does that make sense?
No.
Okay. Well, I think we'll have to come back to that then.
Fair enough.
Let me try. Okay. Is one is just straight motion, linear motion, and one is circular motion. One is actually covering distance. The other one's just going around in circles. Is that correct?
Yeah.
So there you go. Yeah.
Okay. I mean, I don't. We can move on. I don't want to. I'm not trying to derail you out.
No, you're good. You're good. We'll come back. No, dude. Like I said, I do not mind, because the higher level I can get, the more accurate I become. So if you feel like I'm grossly misrepresenting something, please jump right in, bro.
For sure.
All right, cool. So this was another look at the old kinematics. So just to recap on what these are describing, right? Change in position over time, change in position over time. Oops. Dang it. There we go. Or maybe I should do it from this one. Okay. All right, so before we look at the Wang experiment, we're going to look at Sagnac's apparatus. his configuration. So earlier in special relativity, it was put forward that any closed polygon.
What? What are you talking about? Are you
Yo,
fucking
Andrew,
with me?
you're hot, Micah. We were told that any uniform transitory motion, his equations would apply. So if you're in an inertial frame, the speed of light is going to be the same. And as a consequence of relativity, you're going to experience a little link contraction and time dilation as a function of the square of your velocity. So what Einstein says that it doesn't matter that this configuration isn't symmetrical. It can look like this. It's totally fine that the area that light travels makes a non-symmetrical polygon. And as long as it's in uniform rotation, that his equations should apply. So if you were to apply Lorentz symmetry to this, and you put an observer at the center of the device, and you put an observer at the rim, and you said that the angular displacement, due to that motion of the observer along the edge there, is going to cause a fringe shift pattern. Or well, actually, because they're inertial observers, they're both going to predict that the speed of light is the same. So as this apparatus makes its rotation, and because we're not using absolute space to assign for imaginary velocity vectors, we're not preserving absolute space to make the measurement with respect to that. So when this light completes the circuit going with and against the rotation, it's going to complete it at the same time because of the constancy of C, and because the frame as defined by an observer at the rim and one at the center are going to be inertial as defined by Newton's equations and by Einstein's, following that logic, right? Because if you extend any portion of this circle to infinity, it makes a straight line that doesn't deviate much from linear. And that was the whole rationale behind, putting that in the theory, which, logically tracks. It makes sense. So relativity theory actually predicts that there's going to be no fringe shift pattern. And because Sagnac measured a fringe proportional to the rotation of the apparatus, he said, I falsified relativity theory, et cetera, luminiferous ether, optical vortex. When he described the optical vortex, what he was describing and the rationale behind it was he was saying like, well, the ether must be entrained in the earth. And then within the earth, there's, little pockets where when you're in motion, you're going to create a vortex that's going to be, measurable, right? So that's what he was putting forward with that description there. So on Einstein's terms, he falsified the theory as it was put forward. Now we'll get to the solutions that were put forward here and the history of all that. But this is just to start us off with the first experimental falsification of it, right? And we already talked about the configurations. So a Michelson-Morley interferometer, or the classic L shape, or an orthogonal interferometer, sometimes they're called, or a classic interferometer, etc. Right, is just a right angle. And they say that this one is for measuring linear motion, but it can't do that because link contraction, time dilation. And then we have the Sagnac configuration, which is a closed circle most of the time, but it can be a rectangle, triangle, doesn't matter. It can even be whatever shape this is. It's all good. And it will produce the angular displacement amount, right? And they say that one's good, but the other one's bad, even though it was experimentally shown in 2004 by Ruyong Wang that when you have an apparatus and you measure just the effective moving part of it, right, then you will get a fringe shift pattern that's proportional to that motion. So the apparatus is making the measurement with respect to itself. So typically these gyroscopes are wound in a coil around a fixed point, and then they say, in that configuration, they're like, oh, that's that rotational one. That's the one that measures angular displacement, right? Now, what Wang did is he unwound the gyro, came up with a configuration here where it has a linear section at the bottom. That's what we're looking at. And then it has two sections over here that move. The motion of these two sides cancels out. The bottom part's stationary. And the calculation and the prediction is only done with respect to the delta L, which is the effective length, right? And then so instead of the full length of the apparatus, it's with just respect to this portion here, just this top part that moves. So some people will say, well, it was with respect to the detector or the station or the bottom bit, et cetera, et cetera. Well, if that were true, then you would have to use the full length of that. You would have to add more length to the L. You couldn't just use the delta L from the top to predict the fringe shift proportional to just that top portion. So he measured explicitly uniform transitory motion, not in a rotation, right? So this is just rectilinear uniform motion. When we're looking at the graph here, where he's measuring the fringe proportional to that velocity, falsifying the postulates of special relativity about relative motion and the constancy of c. Otherwise, the relativity predicts that there's no fringe here. We have an inertial observer here at this end of the apparatus, and he's sitting at the end here. He's an inertial observer, and then we have an inertial observer here, and these two are in uniform motion. So relativity predicts zero fringe for these lads, and if it well, the fringe that it predicts with the function of the square of the velocity, right? That gamma factor correction or contraction, sorry. So link contraction time dilation would predict a much, much, much smaller fringe than this. It wouldn't even be possible for that theory to extrapolate the velocity that this was moved at to produce that fringe pattern, because the special theory of relativity is a theory of second order corrections, meaning that they're not going to be proportional to the cause of what's causing the measurement, right? So that first order effect, that velocity would be the first order effect, and that first order effect is measured in full in the fringes here, right? So if this was a second order effect, the measured fringes would be much, much smaller, and that would be an indication that relativity theory is true. But it's not. It's proportional exactly to the velocity. So it's outside of the confines of relativity to provide an explanation. And of course, we have the configuration up at the top where he's doing it with against the rotating wheel on the other side of the interferometer arm. It's just, anyway, my favorite one is the bottom one here, the parallelogram. That's pretty damning. So just to recap here, with the generalization of the Sagnac effect, what Wang is showing here is it doesn't matter if light's at a right angle or a circle, it will measure velocity proportional. So what that means is the measurements from Michelson-Morley stand as first order measurements and not as a measurement that produced a zero fringe and then would require a Lorentz transformation out of it to say, well, the reason you can't measure it is because you contracted by this amount. Okay. So you would think like there's a cohesive history, or that you would think that when a man published a paper of that magnitude in 1913, experimentally falsifying relativity, Einstein would have been all over that to hop in and, and explain this as a relativistic effect. Well, he actually never addressed the Sagnac experiment or the Michelson-Gale-Pearson experiment. I think he went to the MGP construction site, shook the lads' hand, but never commented on it as like a relativistic effect or anything like that. Other people always provided that for them, and we'll get into that a little bit here in a second. But what we're looking at here is a paper in 1993 by Nicklaus, who was doing an interferometer Sagnac setup. And they make note here that there's 22 explanations of people trying to provide a relativistic solution for the Sagnac effect with special relativity. And and among them, there was one for general relativity, which we'll come to in a second. But here, this is just stacking up people trying to explain this phenomenon, right? Because maybe I'm wrong, right? Like I'm not. I didn't go to higher education. I don't know. Maybe I'm wrong. But all these people here are trying to explain it as a consequence of the postulates put forward earlier, and none of them successfully did so. And we'll take a look here. We'll go through the history of the.
Hold on.
Mm-hmm.
I gotta cut in. So the Sagnac effect is an effect which can somewhat famously be ascribed to a lot of different effects in different sort of frameworks of how you look at the question. Whenever you devise a particular internally consistent framework, you're going to be able to describe the Sagnac effect. That does not mean necessarily that the metaphysical interpretation of your description is going to be identical in every case. I would, however, disagree. I forgot what I was disagreeing with.
Okay.
Hey, at least I'm honest.
No, you're good. You're good. Well, let's start with the physical fringe displacement, right? Forget about the theoretical. Let's talk about what's predicted. So in an inertial frame, those two lads in uniform motion would experience link contraction as a function of the square of their velocity, right? So a much, much smaller effect than what's physically measured. Would you agree?
No, I would agree that I would I describe that as with the square? I know what you mean. We both understand the gamma factor. It's 1 over the square root of 1 minus v over c squared, the quantity squared. And yeah, so in that sense, but like I think if you actually do the expansion, I'm not sure what order it is off the top of my head.
I would highly encourage you to do the expansion and see what you get.
What will I
Or
get?
not anything that produces a measurement that would explain the Sagnac effect. As we'll find, or
But
as we'll
this is one of those
find as we
calculations
continue.
where you actually don't need to do the expansion because just doing it straightforwardly, entirely analytically, is computationally efficient. So
Well, the theory predicts no fringe, though, like just as a baseline,
nope, that's
right?
not
And
true.
then 1 second, applying the link contraction time dilation, which would be, orders of magnitude smaller than what was measured, doesn't explain it at all. So it's not it.
Which specific experiment are we talking about? Because I feel like you said multiple things that apply in different ways to different versions of this experiment. And the thing about the Sagnac effect is the base Sagnac effect on its own is somewhat difficult to characterize and like to link specifically without the context of other experiments, certainly, to a particular physical model. You need to have it in context with other experiments. For example, stellar aberration. Like stellar aberration is and I'm sure you agree, a hugely important like clue in
Very
predicting what's
important.
going on.
I'm so glad you mentioned it.
Yeah.
Well, in the context of other experiments, which we're going to fully go over and cover, because this isn't even, dude, this is just the surface of it. I can't wait till you see the rest of it. This is so awesome.
Yeah,
But yeah, let's cover stellar ab real quick, right? So 1727, I think it was, or 2029, something like that. James Bradley had his telescope at his 90 degrees looking at stars. And what he found was that he had to tilt his telescope forward a little bit to keep the starlight in the center of the telescope. And what they found was over the course of a year, if you plot out that deviation from that perfect 90-degree zenny, it comes out to be like 20 arc seconds. And when they ratio that against the speed of light, it comes out to 30 kilometers a second. So they took that as proof that the Earth was in motion. And it is a nice kinematic measurement, right? And it's certainly, that angle certainly does ratio to 30 kilometers a second. And if I were a heliocentrist, I would be personally ecstatic because that's the only ratio they've ever got that gave them 30 kilometers a second. But I digress. So after that, though, Arago put a half-covered telescope, or I'm sorry, covered his telescope with a crystal prism. And the hypothesis was that to sort out the matter on if the Earth was in motion or if the sky was in motion, right? Because one of these implies that the Earth is stationary and the starlight already comes in at an angle, which requires the tilt, or the Earth is in motion and that's the cause of the starlight displacement. So we have two possible theories that angle produces. So to determine which one of these hypotheses is valid, Arago took his telescope and half covered it with a crystal prism. And the idea is that when starlight intersected that centerpiece, he would either have to correct it more or not when it hit that refractive media, right? Because it's going to slow the light down, and then the velocity of the Earth is going to have to be compensated to keep it in the center. So he's going to have to tilt it a little further. He found that he didn't have to make that correction angle. And then a couple years later, Airy came along with what we're told is Airy's failure. But what he failed to detect was the velocity of the Earth. So the hypothesis again was that, to settle the matter of why the correction angle for the telescope is necessary. Actually, I have graphics for this. Give me 1 second. We can do the whole thing.
Are
Totally
you going
forgot
to talk
about
about the experiment where they put water in the telescope?
Yep, I'm doing that right now. I'm about to show some graphics for it too.
You see this? You see this chat? This is, people who disagree working together.
Absolutely. Move this over here. All right. Okay. So we have, you guys see that? Okay. Or is it, did I share it on the good quality or the crappy one? Is it still 1080p, boys?
I see it.
It is, yeah, 1080. Yep.
Cool. Fantastic. All right. Okay. So let's see here. So to settle this matter, right, is the scope in motion or is the sky in motion? We had two possible outcomes. And so Airy was going to put water in his telescope, and that was going to be the deciding factor. So if the Earth is in motion, when you add water to the telescope, it's going to slow the light down such that it's going to require you to make a further correction. And the predicted amount essentially was 1 arc second per kilometer for the velocity. So if the Earth is moving at 30 kilometers a second, then 6 months out of the year, you're going to have to tilt your telescope forward by 15 arc seconds. And then as it's going in the other direction around the sun, you have to tilt it back 15 arc seconds. That was the prediction, right? So 1 kilometer per, or 1 arc per kilometer, right? For over the course of a year. And what he found was he only had to correct his telescope by 0.8 arc. So there was a slight correction, but not even close to 30 kilometers a second. And the logical implication here is that the Earth is stationary and the starlight already comes in at an angle. So this is, and this is viewed from the lens of, putting it on Professor Kinkerfuse's theory that, of a stationary Earth with the Earth moving through it, and then any displacement, you would be able to attribute that to the velocity of the Earth. So that's why it's 15, right? So a stationary ether framework. Now, if the Earth is stationary and there's an ether wind, well, we actually predict there'll be a slight drift, and we could absorb that, no problem. It wouldn't be an issue if there was a medium between the light source and us, and that caused the drift. This would be something that's totally fine. But the problem here for the heliocentrist is that they need to attribute the full velocity to the Earth, right? Because that's what they were looking for, confirmation that they were moving with that first order measurement. All right. Let's see. So did I miss anything on?
If you do the calculation, and one of the effects, by the way, that you have to keep in mind here is the Fresnel drag of the water. Oh, sorry, you may not have mentioned. Did you mention the version of the experiment where they pour water into the telescope?
Explicitly.
Okay, yeah, that's what I thought. I just want to make sure. That when you actually do the calculation, I don't like which part of it is not consistent with special relativity.
So if special relativity were true and this water is carrying a velocity of 30 kilometers a second, it's going to require a correction. So real quick here, we have 1 second, pulled it up and then I minimized it. So this is a note from Michelson in his 1887 paper on those results, right? Because you know how we were talking about the undulate or the wave theory and the corpuscle theory too. So this is also a pivotal situation here in regards to that, because he starts the paper off talking about Airy's experiment with the aberration being unchanged for the velocity when water was added. And he says he has a special note here, and then he says, it may be noticed that most writers admit the sufficiency of the explanation according to the emission theory, while it is in fact difficulty of greater according to the undulatory theory. So the wave theory and the emission theory. So the ballistic corpuscle light theory and the wave theory. For the emission theory, the aberration should be less. Hence, in order to reduce its true velocity, we must make the absurd hypothesis that the motion of the water in the telescope carries the ray in the opposite direction. So for the corpuscle lads, they had to say that the light accelerated when it hit the water instead of slowing down, and that's why it didn't correct. And then for the ether lads, they had to say that there was, the stationary ether, mind you, right? But for some reason in the telescope, the ether is carrying the light in the opposite direction of the velocity, and that's why it's creating the illusion that it doesn't need corrected for. So that was where they were at in the 1800s with that. So I'm not really sure.
Fair point. I was unaware of this. So I will
Yeah.
have to look at it and get back to you.
Yeah, dude, it's pretty intense. Like I had a back and forth with someone on Twitter about
Yeah,
this, and
there's a lot of paragraphs here, and I'm not
Yeah.
smart enough to just do a back and forth off the top.
Oh
of my
no,
head.
oh no, you're good. I'm just giving you supplementary information to.
Yeah, no, I'll
But
check it
yeah,
out, and we can
but
talk
yeah,
about
this
it.
but yeah, this in conjunction with trying to explain this through the relativistic lens is like, it just leads to more problems. All right, so there's no velocity potential carried with this water, apparently, opposite or width, and then so that's where we're at with Aries. So we can get back to what's it called, the interferometry stuff. Okay, so let's see the Sagnac effect. It's noted here that Paul Leveuve, that's not how you say his name, but anyways, I'll show it here in a minute. But anyway, this guy in 1917, so a couple years after the Sagnac effect, he shows up and he's like, boys, because the device is rotating, you can't apply special relativity to it. Rotation is an acceleration. And if things are accelerating, you got to apply general relativity to it. So he, using tensor calculus, right, uses Einstein's new derivations for everything to conserve the rotation of the locally rotating Sagnac device into a gravitational field so that it can proportionally get that contraction stuff. But even that doesn't provide enough because the second, because it's second order effects, it's not going to be enough to be proportional to that, even though there's still instead of denying the validity of the theory to apply to the frame, now they're like, okay, we'll apply the framework, but we're still in the situation where link contraction and time dilation predict too small of a displacement. So, and then of course you have the secondary issue. It's like, okay, well, suppose we have an inertial observer in the center of the device for the Lorentz symmetry, and then we have an observer at the rim of the device, which is in rotation. Well, we're in the same situation where they both don't predict a fringe shift pattern because they're both inertial observers. So, so they ended up scrapping that after a while, and we'll come back to the experimental application to that in 1942 with Dufour and Prunet. But that was put forward for a while to put it under the lens of tensor calculus and let the boys transform into it. Oh, Paul Levin, that's his name. Sorry about that. Okay, so now we have some issues here, right? So we've been talking about rotations and who applies to who, because some people nowadays say that rotation of the apparatus means it's special relativity doesn't apply, it's exempt, et cetera, et cetera. Well, there's something called Thomas precession, which we'll get to in a second. But before we get to that, to explain the effects of Thomas precession, which is basically they have an electron orbiting around the nucleus, and they say that because it's traveling at relativistic speeds, there's an anomaly with its magnetic moment or whatever, and it's like precessing a little bit. It's just causing a little wobble or whatever. That's kind of what they say with it. And then to explain that, this guy, Llewellyn Thomas, came along and he introduced a concept called a Lorentz boost, which I'll show the diagrams for that here in a second, but this is to give the history for what Post is putting forward. So anyway, this is under the confines of special relativity, explaining the anomalous electron situation as it has to do with the velocity, right? So it's within the mechanisms of special relativity, right? Velocity. So we're looking good so far. But then in comes your boy Post in 1967, and he's like, yo, check it out. I can explain the Sagnac effect, and I can explain Thomas precession. Here's how we're going to do it, boys. We're going to break electromagnetic processes down into their respective fields, the E and B, and then we're going to put those to a point called free space. Now, I know what you're thinking. There's not supposed to be an ether or an absolute frame that's preferred to be used, but we're dealing with rotation, boys, and times are desperate. So what we need to do is bind these fields to that free space and put it in rotation, and therefore the electromagnetic propagation will conform to the rotation of the fields with respect to that rotating fixed point. And it's like, dang, that sounds like a lot of craziness, man. How'd that work out? Well, a lot of people rejected it because it's not within the confines. It's not mechanistically the same as special relativity. So earlier, Tapioca was touching on the physical mechanism explanation versus the mathematic abstraction of it. Well, what this guy was putting forward, nobody was trying to touch that uh, because what he was doing was essentially using centrifugal acceleration or the centrifugal potential was what he was calling it. Like he was taking that rotation and calling that centrifugal potential and then using that to provide the contraction of the apparatus essentially. And they were like, yo, dog, that's too close to general relativity, using gravitational fields for gravitational potential and stuff like that. So nobody really went with that. And then Ron Hatch ended up doing the math on this apparently, and this apparently does not predict Thomas precession. But I'm not versed enough in the math to break all that down. But it should be noted there was a big contention there from your boy Ron. And then let's see here. I think so. We're good on that. So back to actually, let me show you a Lorentz boost real quick. Okay. So the idea for the Lorentz boost is that, the observer is in it's moving in radians relative to the center point. It's not the same. It's different. Well, what you do with the Lorentz boost is two Lorentz boost is equivalent to one Lorentz transformation. So what they're doing there is they're taking, when you're in rotation, you can have as many infinitesimal, you can break it up into any amount of infinitesimal points as you want for inertial frames. So if you do that and you do that twice, you'll have the equivalence of doing a linear Lorentz transformation. So what he's saying that to explain this rotational effect with an electron, suddenly special relativity applies to that within that framework when it doesn't have to explain a physical fringe or anything like that. Like they were content to apply special relativity to Thomas precession. Now, when you Lorentz boost and you apply that to Michelson-Morley, right, you don't get link contraction and time dilation in the same respect. So it doesn't explain that. So it's just like introducing a coordinate system rotation versus like a meaningful it's not meaningful in my worldview, but as opposed to the meaningful physical mechanism of link contraction and time dilation offered by the linear transformation. So it gets into conflicts with that. And then let's see. So Post was trying to, rectify all this and make everything cohesive. But again, it's like when you start going, oh, well, we can apply it to rotation here. Well, then it fails in other places and it's just not mechanistically cohesive. So, we're in, let's see, what year was that? 67. No answer from him in any meaningful way.
Question.
Yes.
You covered a lot of topics since last time we spoke. Are you saying that Lorentz transformations or special relativity do not apply if you're in an accelerating frame?
So the argument that was made, and especially when I talk to people about it now, they're like, is the argument that they'll put forward is they'll say, well, the device is rotating and rotation is an acceleration and special relativity doesn't apply to accelerations. It only applies to uniform.
Oh, that's wrong. They are wrong.
I mean, I completely agree. So
Yeah.
these are the links I've had to
You and
go
I are in
to.
agreement on that. They are wrong.
Yeah, these are the links I had to go to figure out like who's right. So
no, it's actually a very common misconception that accelerations are not applicable in special relativity. So in special relativity, what is required is that, like, as I understand it, and like I could be wrong, okay? I'm not the world's authority on relativity theory by any means. But as I understand it, special relativity applies when the space, the physical space, X, Y, and Z, not time, not space-time, but when space is flat. Which means equivalently that any triangle that you draw between 3 points in that space will have an interior angle that sums up to 180 degrees. That's like one way of identifying if a space is flat. So you can absolutely have acceleration, and you can treat it completely fine. You just do an integral in the context of special relativity, and you can do things both rotational and with linear acceleration, or a combination of the two. What you can't do,
Dude, no
apply it to a
way. That's
Huh?
awesome. No, I'm
Yeah,
just blown away. I had no.
go on.
That was just the craziest thing. They blah blah blah. You're just like, nah, it's just an integral. Okay, dude, that's awesome.
I mean, it to be fair, just an integral is, if you don't have access to something that can approximate it with by cutting it up into a whole bunch of really small, fairly easy arithmetic problems, which is just what numerical integration is. Very useful, very useful. But if you want to show a mathematical identity, it is only a guidepost. It's not going to get you to a proof, you know.
Yeah.
Numerical
Yep.
integration. But integration
Dude.
is fundamentally a very hard problem, because you're trying to undo. You have to compute an antiderivative, and those aren't even always well defined. The function f of x equals x to the power of x does not have, as I understand it, a closed form antiderivative.
Dude, well, that's beyond me to know what you're talking about, but that is super interesting. I will definitely have to come back and look into that, because that's so funny, man. That they're just like, no, it's a different frame, can't do it, can't be applied. You don't know what you're talking.
Yeah,
That's that's awesome.
yeah, it's definitely, like, it's a thing that I have found in, and like you can tell a like competent, really like well-read resource, like a textbook. Like, some textbooks get this wrong, and the textbooks that like don't get it wrong point it out, because they're like, yo, hold up. This is a thing that a lot of people misunderstand, even in physics. So yeah, anyway.
No, you're good, bro. It's awesome. All right, so let's see here. We got where were we? I think this was, we'll just read here and see what we find. We imagine an infinite, oh yeah, so this is precession. So we imagine an infinity of inertial systems moving uniformly relative to the laboratory system, one of which is instantaneously matches the velocity of the particle. The particle is thus instantaneously at rest in the inertial system, and thus can be connected to the laboratory by Lorentz transformation. It is assumed that the Lorentz transformation will also be described with the properties of the particle in the rest system as seen from the laboratory. Very nice. All right, so yeah, that was just further reiterating that despite the claims, you definitely can get rotation in there and acceleration. Very cool. And then, well, you know what's interesting? You mentioned the flat space-time metric. They actually so you know, in general relativity, they have the curved space-time metric and they can have a flat one. Well, they'll actually use the flat one to derive that stuff as well. It's like they're already imposing it, you know. They're already going special relativity, right? They already took it to an infinitesimally flat plane in general relativity. That's insane.
You are very often, hold on, you are very often able to derive results from in the limit of small perturbations, when you only have to consider the linear contribution, and then like look at that and compare it, one, to observations, which is like what physics is about, and also look at and explore the internal consistency, which would be what mathematics is about. And that will reinforce and then often provide a pathway for a rigorous derivation that isn't based off of sort of mathematical intuitions. A lot of results are first derived from intuitions that aren't necessarily rigorously defined, but a lot of them are then later backed up with rigorous mathematics. The Dirac delta function is a great example. The best example in history would be calculus as a whole. I mean, calculus wasn't well founded rigorously until analysis was thoroughly developed in the 1800s. So,
shout out to the boys, Levi, Savita, and something Cabastro.
Mm-hmm.
Let's see.
Riemann.
Oh yeah, and that guy too. all the lads got together and calced out. Rock out with your calculator out, I think was the motto. All right, so we got the Sagnac derivation here. The displacement in time, or the change in time, the delta t is equal to 4a times omega over the speed of light. So this is just showing the length of the apparatus times the rotation, and over the speed of light is going to give you that angular displacement amount. And and this is the classic derivation for it, right? So this is just a ratio of velocity over c to give you the predicted fringe amount. Now, in special relativity, if you took an apparatus that was 1 kilometer long and rotating at any velocity you want, you could never get it to produce, you could never get special relativity, length contraction, time dilation to produce enough of that to cause the physical fringe that's measured by the rotation of the device. So the point made here was by A.G. Kelly, and he goes into the math over it. I just gave like the truncated version. But what he's saying here is that, due to the magnitude of the second order effects, you are never going to be able to mathematically facilitate that fringe pattern out of that theory, because it's a first order effect that's directly proportional to the velocity, whereas time dilation and length contraction are functions of the square of the velocity. Let's see. Let's see. So surely a hero will emerge and explain the Sagnac effect as a consequence of special or general relativity. Did it ever happen, boys? Well, unfortunately, no. But we did have a quick introduction of the general theory to swoop it up for a little bit. So we're going to cover the brief history of general relativity in Sagnac. So the first introduction to what he calls curved linear, right? So straight, but also curved. And this is the idea that you're moving in a straight line, but reality around you is curved. So unless you could take the perspective of some like God frame, you would see from your reference frame, you would be moving in a straight line. But in reality, from that fourth dimensional perspective, you would be moving along the curvature of something, right? So, and this is where the term curved linear comes from, but obviously a contradictory term, like relativity of simultaneity can't be simultaneous and relative at the same time. So they tried to, and this is a quick look at geodesic. This is one of my favorite parts of relativity. Whenever I look at relativity videos, I always look to see who has the coolest geodesic path in their thumbnails, and that will be the video that I watch. So this is just what I was talking about earlier. This is us looking at.
I want to reaffirm that and say that I completely agree with that metric.
Nice. So this is the what that curved linear path would look like from the God frame. So here we have a photon in a straight line, but Alan, it's going in a curve. Well, I know because we're in the God frame. But from old photon here, this would just be a straight line. And so this is what this is supposed to represent with curved linear and curved space-time and all that kind of stuff. So we're going to look at the Dufour and Prunet experiment now, because, an application of general relativity and acceleration in the rotating frame, this curved linear situation is supposed to produce a result that explains the Sagnac effect. So in 1942 or thereabouts, some French lads, Dufour and Prunet, got together with a specially configured Sagnac apparatus where the top half is stationary and the bottom half rotates, and it's separated by centimeters, I think it was, and then 45-degree angled mirrors. So what it's doing is they have a source on the lab wall and a detector on the lab wall, and they also have a detector on the rim of the rotating device. And what they're doing here is they're testing to see if the fringe shift pattern will be translated to the inertial observer on the wall, right? Because there's some contention here that, well, the device is rotating, so it's a non-inertial frame. And of course, what determines the inertiality of a frame, you could say, is where the observer is, right? Is the observer in motion or is he stationary? So that's quarter being on the rotating apparatus. They say, oh, that's a non-inertial frame, so blah, 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 even though Tapioca already went over the relativity theory in there through the special theory and make it apply. that. But anyway, let's see what we got here. All so if the source interferometer that's and then it hits a 45-degree angle, and
Alan, you're getting a little bit robotic.
I second that. I wasn't sure if it was just me.
testing.
Nope.
I think you said the word testing, but I'm not sure.
You're literally gone. Ether has absorbed all of Alan.
Goddamn Sagnac effect.
Yeah, we should do another velocity correction that's not the Sagnac. That should correct us out.
You
Hold
know,
on.
somebody is probably mucking around behind the scenes with their weasel words. Wait, shit. I'll see myself out.
Nope. Nope. Yeah, bro, what is the internet or something? Satelloons.
I think the GPS has got to do its second order derivation adjustments or something still.
That's probably related to the undersea cables that we're actually transmitting our current conversation, but I'll work it out in the math later.
Yeah, don't worry.
Says
I'll
he's
clean up this.
rebooting. He'll be back.
I'll clean up this bandwidth mess. I got it.
I hope so. This is like a super geek fest. I was imagining, what was his name? Urkel in this. This is awesome stuff.
Dude, Urkel would feel uncomfortable in this geek fest. He'd be out geeked, like looking around, like what's going on.
Wait, hold on. Who are you guys calling a geek?
Oh, I'm sorry, nerd.
Who are you guys calling?
Okay.
Hey, I call myself a geek and loving it.
I'm playing with you, okay? Like, I've clearly been the prototypical specimen.
Usually people who rally around that. I wasn't prepared for an aggressive follow-up or whatever.
2 days ago, this Montreal guy had me losing it at like 9 in the morning. He's like, Bear, did you hear? They're landing a brick on the moon. And he sends the video.
That's a thing, bro. I didn't make it up.
What, like a solid chunk of like concrete or cement or whatever that is used to like build a thing? They just put one of those.
Yeah. Yeah. They
Wow.
call it a test mass because they couldn't get something to work properly.
Well, it's probably okay. To be fair, there's a lot of difference between a test mass
To be fair,
and a brick. One of them is a lot more thoroughly characterized than the other. Otherwise, it's a terrible test mass.
No, it's literally a brick. Literally a brick.
It's a very well characterized brick. There's
Yeah.
an important distinction between the two. That's my only point here.
Well, they're putting it there because they couldn't get their apparatus ready, right? Since we're killing some time here. So it was a failure, actually. It was a failure. They couldn't get the thing that they wanted to be aboard, right? So they figured, okay, let's just say and call it a test mass.
Okay, that I can actually believe. But what was it for?
I believe, if I'm not mistaken, it was a certain lander, but that certain lander wasn't ready.
Yeah, but like the instrument, like the specific instrument that, because like these things that they launch have like 85 trillion different parts. Okay, I mean maybe like 85 different parts. And all of those different parts themselves have like a whole bunch of, and I don't mean like the thing to like get it to drive around. That's like one part. The actual like basic functionality of like, oh hey, the rover has to rove is like one or two parts. And then on top of it, you have all these instruments. And I'm asking which instrument was the one.
Well, I think it's the complete rover. The complete rover wasn't ready. If my memory serves me well, it was a certain rover that was supposed to go and check for water. before the landing of the Artemis. I think it's coming back to me slowly now. It's kind of late. Forgive me.
No, that's fair.
And instead of so they couldn't do it, right? The rover's not ready. So instead of like scrapping it completely and looking bad, I believe they just gave it over to another company, and they said, okay, we'll put a brick, like a big cement brick, and test if we can actually do it. Something like that. Something ridiculous. Yeah.
All right. Well, that's hilarious.
Yeah.
Like
Oh, since
9
we
in the
got some
morning.
dead
Yeah.
air.
Well, I
Oh.
wanted to. I just wanted to say. I wanted to say real quick, Tapioca. I hope this is all right to say. You have said this on live stream, so I hope it's all right. But you are like Van de Graaf's grandson or great
Yeah,
grandson.
and it's totally fine. Yeah, no, my full name is Michael Jemison Van de Graaf. I am Robert Jemison Van de Graaf's grandson. He's the guy who invented the Van de Graaf generator. You put your hand on it and your hair stands up, unless it's humid.
No
Which
way, bro. Nice.
Yeah, yeah.
yeah, and I'm his only descendant who went into physics. I'm a physicist myself. He died in like 67 at the age of 65. He was born in 1901 and he was my grandfather. I'm only 32, okay? I'm not that old.
I think I saw you, Tapioca, on a Schooling Glovers episode, or maybe it was a different debate.
I can imagine that. I have done one debate on MDD. It was myself and I think it was Grayson from Based Theory.
Hello?
It was us against, I think it was Flatzoid, and I can't remember the other person.
Winston, I
I
think.
think
Alan's back.
Yeah,
it
we can
wasn't
hear you,
Winston.
Alan.
No, it wasn't Winston. Winston, I would know.
Maybe not. Maybe
Actually,
not, Alan.
you're still roboting, Alan, but we can. Yeah, really hard robot, but we can kind of hear you. But robot, yeah.
Yeah.
What a
coming back
shame.
in.
This was super cool, man.
We might need to take the pocket protector out, Alan. I don't know if it's affecting something.
Are there any globular tears around? I find that when stuff doesn't go well, you can grease it up real well and use it as like, lubricant or whatever. It seems to. I don't know, any globers here?
Well,
I don't know.
Tapioca, what do you think of the Van de Graaff generator? Can like change the essentially the gravitational direction, from down to up. What do you think about that? With two
It
with
can
two
change the
two
gravitational
Gaussian
force.
surfaces that create like what do you think? And you've seen how that's been applied in terms of these discussions. What do you think of that
I
application
think
of it?
that it is very transparently and obviously a very bad example of what you're trying to make it an example for. It is not modifying the gravitational force. It's affecting the net force, but if you push on an object, that doesn't change the fact that it wants to kind of fall down.
Well,
In
but
the
it's
actual
using like a static charge from the actual environment to
it's
change the
electromagnetic.
actual direction of what we call gravity, essentially.
It's not. No, it doesn't change the direction of what we call gravity.
Well,
It
you could
changes
say it
the direction
counteracts it
of
if
net
you want to
force.
say it counteracts it,
I'm
but
gonna say that it changes the direction of the net force on the object that you're testing.
yeah, that's fine.
That's
But
what
it's
I'm
still,
gonna say.
but the net result is that it is changing. It's adjusting, modifying an independent variable, modifying the material and its effect of what we call gravity, of falling to the ground. Meaning it
No, it's
modifies,
not.
changes that.
It's not modifying gravity. It's adding an additional force. You have multiple things going on. It's not changing the gravitational part of the things that are going on. The gravitational part has nothing to do with the rest of what's going on. It requires very few things to describe. It requires the mass distribution, and that's basically it.
Well, okay. I mean, so if there was a rock on the ground and then somebody goes and picks it up, then yeah, nobody would necessarily. Well, okay, somebody might say you're going against gravity, but in general,
Fair.
one would agree that the effect of what we call gravity, if downward, is still there, even though you picked the rock up and went against it. So you're trying to say that the Van de Graaff generator is doing that in a way, like it's lifting it with the static charge, and therefore not tapping into what you currently believe to be some sort of a downward pull or a downward flow, as it were, in terms of gravity?
Yeah, I would basically agree, as far as I can tell, 100% with what you just said about my position.
All right, yeah, I was just kind of trying to steel man it just to understand.
Yeah, and I could tell. That's why I'm saying that.
Yeah. All right. No, I'm just curious to hear your viewpoint on it. Yeah.
Gio, could we try changing the channel bitrate if it's at like 60 down to? I've done this on like other servers that I mod on. You can like right click the channel.
Yeah, it's probably not that. It's probably Alan.
You think it is?
Yeah,
If
almost certainly.
everybody else is doing
Ah.
fine,
Yeah.
Oh, he said it's
Yeah, he
not,
did
like,
reconnect, but
fully
maybe he reset again. He reconnected and then dropped out.
Yeah, he just messaged me. He said his net is fully out.
Yeah. Yeah, he probably. God damn it.
Well, Mercury is like going retrograde, like right now. So
God damn it.
This,
let me see how
well,
tight it is. Well, it's stationing. I don't think it's gone retrograde yet. Yeah, it's stationing. It goes retrograde in 2 days, which means it's right in the station for Mercury retrograde, starting the cycle.
well, if a eclipse of the sun and the moon interceding can cause electromagnetic gravitation waves to emanate out to cause the effect in a pendulum, dude, I'll buy that 100%.
None of what you just said jives. Sorry.
So you're a physicist, Tapioca, you said?
Yeah.
Cool, cool.
Are you a physicist because of your grandfather? Because of it?
That's an interesting question. I think generally the answer is no, but I don't know what, like, if my grandfather hadn't been who he was, would my dad have decided to major poorly in physics in college? He became a lung doctor instead. And would I have been raised with that particular sort of focus and like intrigue? Maybe I would have become a chemist or something. So I don't know, maybe.
Do
Are
you
you a
own
theoretical
a Van de
physicist
Graaff
or
generator?
sorry?
No, I'm an experimental physicist. So my bailiwick is ultra cold atoms, and specifically using ultra cold atoms to create precision measurement devices using atom interferometry.
Do you dabble in cosmology at all?
So we're trying to make a gravitational wave detector in the long run. But we're the people who like, if you were to make it an analogy to like the Hubble Space Telescope or something, I'm like the people who like kind of make the mirror for it. And not like Hubble did, because Hubble, they messed it up in Hubble. It's a really famous and embarrassing mess up. But I'm more like them than the people who are like, oh, these are the fundamental theories of reality that we're testing. Because I'm an experimentalist. I'm not a theoretical physicist.
So you're not a theoretician, but yeah, the Hubble mirror thing, you call it a mess up. I would say that was a double dipping money grab.
Yeah, I mean, I suppose that's possible.
Well, like, I mean, Robert Van de Graaff, I mean, he won like several awards in physics, the Tom Bronner Prize, the Duddle Medal Prize. And then I didn't know this about him. I'm just seeing this here, that there's a crater on the far side of the moon named Van de Graaff. So that means your last name and your grandfather, that you personally talking to us right now, technically they've named a crater that's your same last name, named after your grandfather on the far side of the moon, which does it exist or not? But nonetheless, I guess you got a crater there.
Fun fact about that crater, it's one of, if not the most radioactive crater, like of that size on the moon.
Now I kind of want the dark side of the moon to exist because I like Tapioca so much.
How dare them put his grandpa on the dark side of the moon?
He's over there with Pink Floyd, rocking out.
Well, so
Yeah.
I have been told, and actually, so at this point, actually, it's been long enough that I should be able to double check it, but I don't actually know how. But my dad was told by multiple people, it like multiple, physicists in the community, that my grandfather was nominated for the Nobel Prize, but he didn't get it before he died. He was the only inventor of a major type of particle accelerator. You have Lorentz, you have Krakoff, you have Walton. All of them got the Nobel Prize. My grandfather didn't. Okay, this is a conspiracy, I tell you. I'm joking, but like, am I totally joking? Maybe not.
Yeah, he should get his just rewards. What the heck? You're right.
Well, is there a level to where they give it to the people who play ball more than others, or is that?
Yes.
Yeah.
No, yeah, he didn't. So he was never made full professor at MIT. He joined MIT faculty in the early 30s and maybe even the late 20s, something like around then. And his first graduate student, who became his lifelong friend and also his business partner, I'll give you guys 3 guesses as to what this guy's surname was.
Was he one of the top 5 barons?
Not at the time.
Hmm.
So is Alan having like a full outage, or his whole internet's out?
The last message he sent to me was, I said, SGO changed the bitrate. He said it's not that. The bitrate's fine. My net is like fully out. And that's the last thing he sent to me.
Yeah.
6 months ago. Yeah, he just had internet.
He said internet outage, not a power outage.
He just said my net is fully out. And then I said maybe hotspot from your phone. But that's like super low bitrate or bandwidth too.
Man, Alan always does this to me, just constantly edging me. It's terrible.
Yeah, I was close. I was close.
What, edging you closer to becoming a flat earther?
No, I meant sexually, sorry.
Oh, okay.
Yeah, you asked for it, bro.
What did your grandfather? What did Van de Graaff think of the shape of the Earth?
It would have, I'm sure, been completely baffling to him that this was even a thing that people actually found confusing.
Well, so if he was born in 1901, I mean, did you ever taught like he was taught the globe? Because not everybody was taught the globe back then.
He was. I mean, he grew up in like a plantation. So if you Google Jemison Van de Graaff Mansion, and Jemison is my middle name, Van de Graaff is my last name, but if you Google Jemison Van de Graaff Mansion, that is the house that he was born in and grew up in. And it's a house that has a website. Okay, that tells you something. Like, whose fucking house has a website? Exactly. Fucking, I wish my house had a website. But
So how did his parents make their money, or where did that money, or was it just old money?
so his father was a lawyer, and his father, I think, was also a lawyer, and his father. Eventually, you get back to before the Civil War, and then they were like slave-owning plantation owners. It's
Yeah.
not, it's not
It's
ideal.
old money. Old money, yeah.
Yeah, no, so my family was totally old money. That money got 90% wiped out in the depression. Not 100%, but like 90%. And my grandfather's success as a physicist and scientist who actually was like pretty well known. I mean, everybody knows the device I'm describing. Like literally everybody. So
I just got a update from Alan. He said reset net now.
All right, boys, we're back.
Oh yeah.
fuck
Let's
yeah.
go.
We're
Let's
back.
go.
Sorry about that delay. Give me 1 second. Let me get the streams going.
If
We're
you gave me
restarting.
like like 2 more minutes, I was gonna be able to completely shut this thing down. I was trying to sabotage you so hard.
Nice. Nice.
Yeah, we just learned that Tapioca here is actually the grandson of Van de Graaff.
Yeah, dude.
You knew that?
Boy, Vandy.
Yeah, no, I've known Alan longer than I think any of y'all.
Really?
Yeah. We met through Pitch Lumen.
Yep. Old
Okay, so
pitch.
are you here because you knew he was going to be here, or you just happened to be here?
I just happen to be here. This is one. So I keep this particular channel actually. Currently, it's number 3 on my sidebar. But like everything that's in the top 10, I basically gets equal eyesight from me because I like coming here every so often.
So how long
Nice.
have you been a flat earther?
I'm not a flat earther, man.
How long before you become a flat earther?
Uh,
I like that question.
If I absorb the what's it called? Nah, never mind. We'll not get into that. Anyway, whenever you guys are ready to continue, my stream's on. My stream's good to go. So if we can jump back into it, I can finish this bad boy off. If you guys are still down.
Nah, we're over it.
Yeah,
All right.
yeah, I reshared it. Yeah, good to go.
All right, cool. All right, so to pick up where we left off, we were talking about general relativity and its application for the Sagnac effect. And then we were looking at an experiment that was done where an observer was fixed to the lab wall, and also there was an observer at the rim of the rotating device. And what they found was that the fringe was measured by the observer fixed to the lab wall. So there's some mechanism, right, that's causing the path length to be fully, or when the path length is increased due to the rotation of the bottom half of the interferometer, there's some preserving aspect of absolute space that's making that inertial lad on the fixed to the lab wall make that measurement to keep that consistent with the velocity of the rotating apparatus. So here's some cross sections of what the light paths would look like with the 45-degree angle. So you guys get a nice visual of that. We got your centerpiece of the axis of rotation, and then the 45-degree angled mirrors to facilitate that up and down translation there. And then here's the worst picture ever taken of the apparatus. And so that's what we're looking at here. Bottom half rotate, top half stationary.
What the fuck is that?
Yeah, it's not great, but somewhere in here is a lad fixed to the lab wall, presumably.
Yo, I gotta say, I'm looking at this thing. All I see is 3 ghosts that look like they're at a pack. Am I wrong?
Yes. No, that's that. The original Sagnac apparatus is actually 3 ghosts. So you're dead on. So the measurements that were shown from this configuration, the classical theory predicts for a fringe displacement of 0.53 fringes, or 0.053 fringes, and the relativistic theory predicts 0.05 fringes in the configuration with the lab wall observer versus the what do you call it?
Ghost potato observer?
Yeah, versus the ghost potato observer on the rotating device. So for those of you who aren't familiar, but this is an incorrect prediction, right? The inertial observer should always be measuring CSC. There should be no reason that the translational speed was preserved through a measurement of absolute space. That's not supposed to happen in relativity theory. So this prediction is way off here by a factor of 10. And Paul Levov's explanation was, hey, man, because general relativity is a theory of gravitation and this device is in rotation, there's going to be that inward attractiveness. This is his rationale for it. Therefore, we have to use the center of the device as the preferred frame for the calculation to be done. Because if you invoke the center of the frame, you can, quote unquote, make the same prediction there. But even though they, even though they don't do that, I'm sorry, they can't do that because then they're invoking a preferred frame, right? They're invoking a stationary frame to make the correct prediction when the general theory is about general covariance, and this explicitly should be covered in its it should definitely be able to make this prediction as is if it's going to follow a general covariance, meaning that it doesn't matter if the frame is accelerating or not, it should still make the correct prediction. And let's see here. Unlike what we're kind of half told about special relativity only being applicable to certain types of motion.
I will
and
take
then-
credit for the other half of that half told.
Nice, absolutely. And yeah, you single-handedly, pretty much, you and our boys Solzy, who put together that math for the different types of motion all being the same. So shout out to that guy. So you and him are the two. Anyway, we'll see here.
God damn robot.
Roboting.
Right? Has your internet did it go red again?
Yeah, you know what I do.
No. What? No one heard what you wanted to do. Ether has disallowed that. Man, this is such a good presentation too.
For real, bro. Yeah, just really enjoying this. I wanted to ask,
Testing.
how do they get the same thing with rotational and linear?
Sounds like you're
Still
back.
don't quite get that.
Alan, say something. Are you back?
You might be back.
Testing.
Yeah, good.
Sounds good. Go forward. Don't waste time.
Yeah, cool. I'm just gonna finish out the rest and upload the recording later. I think I'll just save the bandwidth for Discord. So, what was your question, SE? How is it making a different prediction for the two types of motion?
Well, not different. You guys said it's the same, rotational and linear motion. You did the math somehow, or did I not understand it correctly?
Yeah. So what's being measured in the speed of light, like the way that it maths out, right? Like they don't derive it like, oh, this is a specific type or whatever. Well, I guess they do in the equation, but that variable that's used to differentiate between linear and angular was experimentally shown to be equivalent. In other words, it doesn't matter if you're rotating or if you're moving rectilinearly. It's all the same.
I get that part, but how? How was it shown?
How was it shown? Through the fringe shift measurements?
Okay, gotcha. Okay, so they actually measured it. Okay, gotcha.
Oh, yeah. Sorry. So, yeah, that's what Ru Yong Long was doing in 2004. So when he was moving his apparatus linearly, he got a fringe shift proportional to that velocity.
Okay, cool. That clears that up. All right, perfect.
Yep, no worries. Yep. And then, so we got the prediction for general relativity being off, and then they basically wrap that up, and nobody really tries to explain it under general relativity now. There is a project right now called the Ginger Project where they're trying to bring general relativity back into it. I think the acronym for the project is something like, it's like general relativity and underground gyroscope something. It's one of those weird things, but anyway, they're trying to wrap it up into the relativistic confines and stuff, and maybe we can cover that towards the end. But we're going to move on from the rotating apparatus making the wrong prediction for a locally rotating device, and now we're going to look a little bit at a phase conjugate mirror, which I don't have a diagram for. Give me 1 second. Let me pull that up. PCN, that's not going to know, a phase conjugate mirror. And shout out to Tapioca, who also helped me with this concept here. So the difference between a regular mirror and a phase conjugate mirror is that when you send out a wavefront and it gets reflected by a material object, it will that wavefront will not be like, you can't guarantee that wavefront is preserved or it's the same as when the signal was sent. Globe Dom, your hot mic brother. And so anyway, there's no guarantee that you could preserve the wavefront. So they're like, oh, we don't know if the Sagnac effect is due to a change in the two.
It's not just that you don't know if it'll be preserved. You actually generally know that it will be reversed, because like if the part in the middle, if you have like a cone,
Yeah.
like on the diagram, if you have a cone and it's going in, then the tip of that cone is going to be the first part that's coming out, so it's going to be reversed.
Gotcha.
Whereas the actual shape of it in, an agnostic frame, I suppose you could call it an absolute frame if you wanted to, would look at the figure on the right, and it would be the same shape of the wavefront going into the phase conjugate mirror as coming out.
Yep, absolutely. So a way you could look at that is they send the wavefront out, and then it's kind of just traveling backwards in time, so to speak. You could look at it that way. So this way you can guarantee, using this special mirror configuration, it's going to reflect it back in a way that preserves the wavefront. That's the most basic explanation I can give
Yeah,
for
a
it.
reflection in time is actually a very good way of visualizing it. Yeah.
Awesome. All right. Muted you for a minute, Globe Dom. Love you, brother, but that hot mic is crushing me. Okay, yeah. So phase conjugate mirror. So in this configuration here, what could be said is that what they were trying to figure out is the speed of light changing on the two-way speed? Is it slower on the one-way? How is this measurement for the fringe displacement happening? Now, so in this orientation, we have it configured in a loop. So it's coming around the corner here, and on the one-way speed, it's showing that the wavefront is already displaced in accordance to produce the Sagnac effect on the one-way. So this would be like a one-way measurement of the speed of light not acting in the way that Einstein predicts it for an inertial observer. So so this is the fringe displacement that they got for the for that reading, just showing that it is out of phase and all that, proportional to the velocity on that one way. And then a review from Ruyong Wang, he's showing, hey, do you guys know that if you extend this curved portion of the interferometer out continually, it'll eventually be a straight line, and therefore the one-way speed of light, in a linear reference frame is being shown to not be in accordance with relativity theory. So that's a cool way to look at it. So extending that curve to infinity, it's eventually going to flatten out, and that's the whole reason, the rationale behind making it apply in a closed polygonal circuit in uniform rotation, because it's when you get to that extension of infinity, it's not going to deviate from a circle, or
But
deviate from linear.
That's not true.
Oh,
it is going to, you are always, if that line, if that arc subtends a certain angle of a circle, and you just extend it out in a Euclidean space, you just extend it out, it's always going to subtend the same amount. Its curvature per unit length is going to go down, but that's different because you still have to integrate over the whole thing if you're actually going to talk about motion and paths over the whole thing. So it's not going to just become like a straight line. It's, if you start out with a 1/100th of a circle, like circumference, and you extend it out, it's still going to be 100th of a circle, unless you're in a situation where there's a whole bunch of spatial curvature, which, unless you're around black holes, is not really how things work.
well, I think
You beat
the
me to the mic. I
the,
was thinking the exact same thing. How is that ever going to straighten out? Yeah.
Yeah. The rationale here is much simpler. So as we were how we were discussing earlier, right? It's just the change in the motion, like it's going to be in a different spot. So when you're extending this to infinity, right? It's just going to be the same. Like it's not going to be any different. So this segment here, like it's just describing the same thing as what he's showing you, right? There's no difference between the two, even though you could look at it, analytically like that. But the measurement itself in regards to the motion, right? It's still measuring that same thing.
In the figure on the right, which is the one that has like different portions of time, I guess, as the wavefront expands.
Mm-hmm.
So that figure does not represent the same chunk of the wavefront, because you're cutting out like the in the top when it's at the earlier time and it's nearby the source, you have it and it's like a sixth of the entire angular circumference of it. You've got a like a pizza slice that's like a sixth, and he doesn't extend it out. He extends it mostly down, but not entirely down, which is an interesting choice. And in any case, you're not looking at the same thing. You're looking at a much smaller section of the same thing.
Hey, buddy.
Yeah. So, in all the same, though, the extension of it is going to have the same effect, right? It's just measuring the same thing, the displacement over time. And it's just showing that the one-way speed still applicable is it's already changed. It's already Sagnac affected, so to speak, before it hits the mirror is the main point here.
That's another thing, bro. Not to be a stickler, but one-way speed of light.
Mm-hmm. Yeah,
For the record,
it's measured in GPS.
I disagree. I do not think it's possible to measure the one-way speed of light.
Well, we will definitely get to that in the future slides here.
Fair enough.
Cool. All right. All right. So this is just Sagnac and the boys showing that in a uniformly rotating frame, regardless of how you interpret it as acceleration or what have you, or linear or angular, it's all the same, all being measured to the same magnitude. And all of the explanations for general and special relativity have not yet produced anything that explains the physical fringe. So let's see here. Before we get to GPS, there was one more thing I'm looking for. Give me 1 second. Well, maybe it'll pop up. Wait, is it? Jesus. Well, anyway, we'll keep going, but remind me to come back to, if anyone remembers, what Post said about the predictions for general and special relativity. We'll come back to that. Okay, so anyway, the boys have shown experimentally that the speed of light is not behaving on the one-way or the two-way speed. Now, if you for the phase conjugate, maybe that's a little ambiguous, so we can come back to that and look at trilateration and GPS for the one-ways. But that's what we're at so far. Is that is that relative motion and light are not behaving in accordance with special and general relativity in regards to measuring motion. So here we have the GPS system, and we're going to get into the missing corrections that should be there. So here we have the GPS tracking station verifies this direct gravitational potential effect upon the rate of a clock. The GPS tracking station requires all clocks to have an adjustment for their height above sea level. Interestingly, they do not require an adjustment for their latitude. The oblateness of the Earth is due to the spin rate is such that the effect of the extra gravitational potential, the greater equatorial radius upon the clocks at the equator, is precisely canceled by the greater equatorial spin of the velocity of the clocks. So what he's putting forward as an explanation as to why there's not latitude-dependent corrections based off of the gravitational potential between an observer or a ground receiver and the satellite due to the contour of the Earth is that it's just offset due to the spin of the oblateness of the Earth rotating through a stationary gravitational field, and it all just happens to work out. So that's their justification to it. So we're gonna come back to that here in a second and revisit the meaningfulness of this correction versus surveying on the ground. So both bodies claim that, or both bodies name, or so these are institutions that give the standards for clock synchronization. One is the International Telecom Union, and the other is the CCDS. I wasn't able to find out what that acronym stands for, but those are the lads that were in charge of clock synchronization at the time when they were building the GPS system. So both bodies, so both of those agencies, name 3 corrections as relativistic. These are: the velocity correction is calculated under special relativity for when transporting a clock, a correction for the difference in the gravitational potential under general relativity, which is outside of the scope of this paper. So he's just noting the correction. So we got that gravitational potential for GR. And then he says they have a third correction that is named for Earth rotation. And the latter correction is the Sagnac correction, and it has nothing to do with relativity whatsoever. In this correction, let's see, it is the correction necessary because light does not travel around the globe east to west at the same time, right? Because otherwise you wouldn't have a fringe displacement for 15 degrees per hour for Michelson-Gale-Pearson and the subsequent experiments after that use a similar configuration and all of that. So obviously there's a preferred direction on Earth regarding east to west propagation that requires a timing correction to make the speed of light equal to the speed of light in the way that they say it is, and not the speed of light plus or minus velocity, right? So invoking special relativity, more still general relativity, to explain the Sagnac effect is like claiming that the bouncing ball of a child requires relativity theory to explain it. It's a simple first order effect, and indeed the presidents of the CCDS right, confirming that it's not a Sagnac effect. So this dude published a couple of papers. He never published the actual letter or anything like that, but he's referenced it a couple of times. He reached out to the presidents of these organizations about these corrections that are made. So earlier we covered a Lorentz boost and a Lorentz rotation. So a Lorentz boost would be link contraction time dilation, and a Lorentz rotation would be that mechanism that was proposed for explaining Thomas precession, where they invert the world line on the coordinate system, and 2 of those is equivalent to 1 Lorentz boost, right? So different mechanistic corrections, but still being applied under the guise of like explaining the Sagnac effect, even though it's clearly outside of the confines of special relativity to explain. But we'll continue here. So here we're going to go over reference frames that GPS use. They use the ECI and the ECEF. I call the ECI frame the ether-centered inertial frame, because what they're doing here is they have a spot with respect to absolute space that they're using to take the measurement in. So this is the first measurement that they take for trilateration. So when you get a signal from a GPS space vehicle, right, that signal being sent is calculated in the ECI frame, and the measurement and the timing is all done off of that, right? So quick recap on GPS and how it works. GPS doesn't give you distances in the traditional sense. It sends electromagnetic propagation out, and it sends its coordinates and the time that signal was sent. So like where it was at and the time, and then you get that information on with your ground receiver, and you multiply that times the speed of light, and that absolute value, if it's negative, means you're going going against the rotation of the Earth, and if it's positive, it means you're going with the rotation. So that's how they do the timing. So basically, it's the timing from when the signal was sent to when it was received, and with the relationship with the velocity of light, they're giving you the derivation for distance, and they're invoking this frame specifically, and they're like, oh yeah, it's with respect to the center of the Earth, blah, blah, blah. And then they take that distance, right, that was derived here, and then they put it back where they already measured it at, right, in this configuration anyway. And they're like, oh, look, this time it was actually just from the satellite to you, and, not a measurement with respect to absolute space. But anyway, these 2 frames are both synced to sidereal time. And the reason for that is it would change the anisotropy effect in the speed of light. So meaning that east-west bias variance, what they do by syncing this frame to the sidereal time, which produces those measurements, right? They're effectively making the speed of light the same in that frame. And then when they transform it out, they have to make corrections for the actual timing difference. So this is where all that comes from. And then when they apply their finalized corrections, look, suddenly you're back on the graticule again. Now, what was found, or before we move on to the significance of the timing and the corrections here, we're going to look at coordinate system simultaneity, because doesn't GPS exclusively mean we're on a ball and graticule and whatnot? Well, all these coordinate systems are equally valid at the same time. So Cartesian, rectangular, cylindrical, spherical. if we lived on a plane and satellites were also on a plane above us, all these coordinate systems could be mapped out. You can scale it covariantly, and you would get results that would put you back on what you think are the ball, but it would just be, coordinate system relative in your interpretation of that coordinate system, right? So that would be how you would use GPS on, or how that would work on not a ball. So here's some more coordinate systems, all being equivalent and being the same. It's like there's no mutual exclusivity based on what they're mapping using a timing system, right? We could live on a trapezoid, we could live on a dodecahedron, and the GPS timing stuff would still provide distances regardless. So for scale invariance, we're going to look at an instance where raw timing signals were analyzed, and it was found that they already are offset with Sagnac corrections in them. And then further, when your device gets them, they make that Sagnac rotation for that finalized correction. So what this means is if you were to try and use GPS to verify distances or falsified distances, or use it to show discrepancies within the system that it's being used in, you would never be able to do so because the timing that you get is already corrected and adjusted, and then you're dealing with additional after the fact corrections that are going to put you exactly back on where you're told that you're at on the graticule. And then you're going to look at that and you're going to go, oh, look, well, it matches, Google Earth, it matches all this, so therefore it must be a ball and all that. But again, the data that you're getting, if it's sent out already cooked, and then your device is correcting to put it, to conform to the coordinate system based off of timing changes and the corrections in that, then, that device is going to be useless for telling you if there's a deception at play. So let's see. So now we're going to touch back on the gravitational potential corrections. So earlier it was mentioned by Ron Hatch that interestingly, there's no latitude dependent corrections for the satellite's position relative to ground observers based on the contour of the Earth. And I'll show what I mean by that here in a second. But let's look at the gravitational potential corrections. So in the history of general relativity, one of the biggest, it is, in my opinion, the most important and substantial proof for the theory, because it would give a physical mechanism for the gravitational field to meaningfully change the frequency in light and give the interaction that's predicted by the theory. So these redshift observations were first done by astronomical means from transits during eclipses and when planets and stars would transit the sun. Planets would transit the sun, Venus in particular. They would take spectroscopy readings and analyze it and see if they could find a shift in the light that would correspond to an interaction with the gravitational field of the sun. Most notably in 1919, there was the eclipse with Arthur Eddington where he went out to look for gravitational lensing. Well, at the same time, there were a couple lads back in the cut looking for gravitational redshift of the same stars, and that would correspond to, okay, we expected this much starlight displacement, and we also expected this much gravitational redshift. So in other words, we could establish a more meaningful cause and effect relationship with the measurements if it could be substantiated that the starlight frequency shift was also in accordance with the prediction of the gravitational field of the sun, based off of its mass and relativity and all that. Right. So this would have been super important for them. But the lads in charge of those measurements, John Evershade and St. John, never made any measurements to correspond to gravitational redshift, in particular during the Eddington observations. And this is kind of like left out of the history of it. And it's more presented that, because of the displacement solely that Eddington saw, relativity is therefore true. And then for about 30 or 40 years after that, there was like a big back and forth in the scientific community on extrapolating meaningful measurements and predictions out of general relativity, because the equations being general nonlinear, they diverge to infinity, so they need to be linearized a little bit and reined in so that they can give meaningful predictions. And they weren't really sure, if what they were extrapolating out was meaningful or not. So anyway, they just had a history of not really producing anything meaningful for a while that they could all cohesively agree upon. And then we come to 1960 and 1965 with Pound-Repka and Pound-Snyder, respectively, where they used an energy emitter to emit electromagnetic energy at the top of a tower and at the bottom, right? And they had a Mossbauer detector. So what they would do is they had a prediction for, or let me explain the Mossbauer detector real quick. So the Mossbauer detector converts or electromagnetic propagation or energy into an electric signal at a certain frequency rate based off of the energy that it absorbed, right? And you could set it to only accept energy of a certain frequency. So with the first configuration, if you know the wavelength and all that of your electromagnetic propagation, you can know the frequency. So they have different. There's a different gravitational potential for the frequency predicted for an emitter at 10 feet above the Earth's surface versus 75 feet. So at the bottom of the tower here, there's going to be a different gravitational potential relative to the top. So with that difference, they had the detector set to only accept a frequency that would be expected due to the shift in flight down to the bottom. And if it's any other amount, then it's not going to accept the detecting, or it's not going to convert it to an electric signal and give them their reading based on that energy or based on that frequency. So the first measurement they got was successful. They were like, oh, snap, boys, we did it. We found general relativity. I'm just kidding. They didn't say that. The title of their paper was The Apparent Weight of a Photon. And what they put forward was that the classic theory and the general theory made the same prediction. In other words, the classic theory would say that the light, would gain speed going down, like equivalent to an object falling at 9.8 meters per second squared. The light would gain acceleration and would therefore frequency shift due to that acceleration, and that would make the detector accept it. Whereas the general theory predicts that due to the gravitational field, like the gradient, you can think of it. An easy way to conceptualize it would just be like a density gradient. So as you're closest to the surface of the Earth, the stronger the field. As you get further away, the less strong, right? So as the propagation is coming down through the electromagnetic field, the speed of light is maintaining the same speed, but because it's oscillating in a denser medium, right? It's going to be a little slower. Is the way that you could conceptualize it to make the measurement work with general relativity. But either way, they detect the same thing, and the detector can't differentiate between the two. It's merely converting the frequency. It doesn't know if the light got there faster or if the gravitational gradient caused the shift. So they did another experiment in 1965 where instead of using, I forget what frequency they used for the 60 experiment, but in 1965, they used a gamma ray, and the reason for that was to eliminate electric and magnetic interference. So the Stark and Zeeman effect were discovered in the early 1900s, and basically that was electromagnetic propagation going through an electric or magnetic field will experience frequency retardation proportional to the strength of the field, and then going with and against the rotation of the field, etc. Right? So a gamma ray would be neutrally buoyant, so to speak. So it's not going to respond to the electric or magnetic fields. So like the apparatus itself, the Earth's magnetic field, all these kind of factors that may have possibly frequency shifted the light in flight. They were using this to control for that. And once again, at 75 feet, this time they got their prediction. But again, we're left with the same issue because it can't tell if the time of flight changed or if the gravitational gradient produced the effect. And they suggested that they should do another experiment and have an atomic clock at the top and at the bottom of the tower so they could time the time of flight and then get a definitive answer on which theory makes the correct prediction. So that experiment was never done, and these gentlemen were given the Nobel Prize for successfully confirming gravitational redshift in the laboratory. And then, subsequent that, everything was kind of reined in on the astronomical scale after this was shown to be, true in the lab. They just immediately started applying it to the sky in a more uniform, cohesive way. So shout out to the boys for getting that one through. But we're still left with this problem with, is the light going faster or is it a frequency shift change? Well, we can definitively know that with vertical interferometers, but it's outside of the scope of this presentation, sadly, which now that I said it out loud, I kind of feel a little remiss that I didn't include it. But we'll continue with the gravitational potential correction argument that Ron was putting forward now that we've established that gravitational potential corrections are canonized in the lore of relativity theory and all that, right? So suppose there's a satellite above Earth and it's at the 50th parallel, then there's a lad there, and that satellite is at his zenith. So it's at his 90 degrees directly above. And the distance from the satellite to him is going to be, let's just give the general story the benefit of the doubt and say the satellite is 20,000 kilometers above the surface. And then the signals are being sent, at the same time. So as this signal is being sent that reaches our lat at the 50th, there's also a signal that's being sent at the same time to a lat at the 45th or 40th, whatever, right? Either way, it's going to be at a different altitude relative to the satellite, which is going to require latitude dependent gravitational potential corrections, which is what Ron was laying down. And again, his explanation for that was, well, we know the Earth's an oblate spheroid and it's rotating through the stationary gravitational field, which is just causing an offset and making it all an equipotential gradient that we can just, ignore fine-tuned corrections, even though in the lab, we're talking about the frequency shift of over a distance in the gradient of 75 feet, right? So if these gravitational anomalies were true, when GPS came out, they would have gone all over the latties and made their gravitational potential corrections to compensate, for this very effect that they gave the lads the Nobel Prize for in the 60s. Now, this has huge implications because they're saying that due to the sensitivity of light in keeping, clocks in sync with their oscillation rate, that these corrections, have to be made, or their GPS is going to be off by, 30, 40 meters, et cetera, right? So they just have this uniform effect that they don't have to correct for with the frequency shift in light. It's just some sort of equipotential gradient that all works out. But on the ground, when the lads were doing geodetic surveying and their measurements were off, and by measurements being off, I meant they looked in the sky, they tilted the theodolite to their zenith, and then they saw that the stars that they expected to be there were off. So they were like, oh, you know what? The gravitational potential in this area is off, and to be perpendicular with it, I have to tilt my device. And then when I tilt my device, it'll be in alignment, with the expected values for the stars and where they're supposed to be in alignment with the coordinate system. And we'll call that deviation a deflection of the vertical that's necessitated by the equigravitational potential difference from the geoid relative to the ellipsoid, right? So that oblateness. So this gravitational model that's been thrusted upon us as an overlay for the ellipsoid that they say that we live on produces these effects that cause a plumb bob to physically need to be tilted because it's not actually going towards the center of the geoid like they would expect. Because of that, there's deviations and they're not actually at true level. And only by tilting their device to get the star in the center of the telescope are they established, right? So this is how all this is derived, right? Classically, to make the WGS model and all that stuff that the satellites are supposed to be using. Well, if any of this were true to the magnitude that it required a physical movement of a device, then that would be, you would have to have frequency shift due to those gravitational anomalies relative to the lattie, and none of those are in GPS at all, and they don't exist. And so what I'm putting forward is that the GPS system takes place over a plane above us, and we're on a plane, and there's an equipotential gradient between us, and therefore you would not need any latitude dependent GPS corrections due to the contour of the Earth. Any questions? All right. So we'll look at some additional corrections that are put forward for the atomic clocks. So this is where they're saying, okay, we have to account for these gravitational effects, the gravitational potential. We have to correct for Earth rotation plus the space vehicle velocity. Now, this is where we're getting into another issue where the space vehicle, now this isn't in regards to sending signals to ground receivers. Right now, we're strictly talking about it, in the conceptualization of the heliocentric model, right, is that there's a satellite in free fall around a globe. And then in accordance with relativity theory, this clock, once it's been synced, is supposed to be in sync, forever because the constancy of the speed of light. It is not supposed to correct for its own velocity as it's free falling around the Earth, because that would be contrary to the Michelson-Morley experiment, right? First, they said that the circular orbit couldn't be measured because it's if you extend it far enough, it's just a linear path and you can't measure linear motion with the speed of light. And then when Sagnac came around and it was shown that you could definitely do that, they were like, oh, you know what? Actually, the general theory is double extra more true. And what's really happening is there's a gravity well that's produced by the sun, and we're in free fall on a linear path through that. Right. So that's where we get the curved linear geodesics, right? So they've completely removed any ability to have an absolute space where something like your velocity in free fall around a body would be measurable, right? Otherwise, we could measure our velocity around the body of the sun in Michelson-Morley. Now, so, this is completely contrary. So what they're doing here is they're accounting for the satellite in free fall around the Earth, exactly proportional to its velocity in the same way that you would derive it for the Sagnac effect. Now, they're not using any relativistic transformations here or anything like that. He's literally showing that that when it's all said and done, what they're accounting for is just velocities, and they're using an equation that's identical to the Sagnac equation. So earlier when we looked at that derivation for the classical prediction, where it's just what is it? 4 omega times the rotational rate. I'm sorry, 4 times the area times the rotational rate over the speed of light. So all they're doing there is just velocity, right? There's no, you wouldn't know if there's like a gravitational potential correction. It's not going to manifest differently, right? What's happening, how an atomic clock works, is that it sends out excited cesium into a chamber, and then electromagnetic waves are sent at the cesium gas, and when it matches the oscillation rate of the cesium gas, which is 9,192,000,000 oscillations a second, they send that out of the chamber and then they ionize it. And by ionizing it, they convert that to an electric signal, which produces their how they divvy up time in that 9,192,000,000 oscillation rate. So the electric signal converted from that gives them that's how they maintain it. So once the radio waves match the oscillation rate of the cesium, they lock that in and they should be good to go, right? But what they found is that they had to add additional energy into the system to maintain the oscillation rate. So there's a retardation in the oscillation rate proportional to the velocity. So an easy way to conceptualize that would be, suppose you have an oscillation rate of 9 billion, right? Let's just make it an even 9 billion, and you're moving at 10 miles an hour. So instead of moving at, or let's just say you're moving at 1 billion miles an hour. So now you're going to be, so now the oscillation rate changes to 8 billion. So you're retarded proportional to your velocity, right? Like 1-to-1. So now they need to interject enough energy to make up for that retardation. So that's not supposed to happen in relativity theory in their conceptualized version of reality. So the fact that happens is, devastating to them, because they have a satellite free falling around, the ECI frame, right? It's falling around the center of a ball. There should be no reason for that velocity correction for the satellite. So anyway, just showing out like what they actually correct for in the system. And then additionally, right, we have ground stations that these space vehicles, they call them, right? I'm just going with the terminology that I read it in. I know space isn't, what we conceptualize it as, right? But anyway, what they would say, what happens is these SVs, as they're traveling along the Earth, they come across these ground stations, and the time it takes for a craft to cross ground stations, they call it meridian corrections. They'll delete time from the clock or add time to keep it in sync. And what that does is that really removes, like I was saying earlier about how if the system's cooked, you're not going to be able to find discrepancies in it while using it. Well, that mechanism of the clock corrections as it passes stations is what facilitates that, or what helps facilitate that. That's what keeps the coordinate system in sync. Now, whether or not there's malicious intent involved, right, doesn't matter. This is what you would have to do to keep the system in sync. So doesn't matter either way. So any additional corrections that they've added or changed or made differently, you would never know. You just have the outputted product that puts you on the graticule, and you're like, okay, well, it seems to be working. So this is going over the meridian corrections for the clocks over ground stations, just reiterating the same thing. So here we're looking at the equations where they're accounting for Earth rotation plus space vehicle. And it's just, things that they're not supposed to be correcting for if the theory of relativity is true. And then here we have Ron Hatch, or I'm sorry, not Ron Hatch. This is A.G. Kelly speaking on interferometry and rotating systems and stuff, because they go as far as to say that, dude, that's hilarious, Jeremy. I feel the same exact way. Let's see. They go as far as to say is that due to the rotation of the Earth, they have to make that Sagnac correction, right, to explain the anisotropy and the speed of light when it's supposed to be isotropic. So they say that pretending that special relativity does not apply to rotation while applying it at the same time to daily experiments like the GPS system, which has a far greater rotation than the Sagnac experiment, is indefensible. So in other words, the Sagnac experiment, if you can't explain it in a locally rotating interferometer, how are you going to apply it to the Earth? That's insane. So he goes on to quote Post from 1967, who at the end of his paper says, to be consistent with the principle of relativity, one has to demand that the Sagnac interferometer and the ring laser cannot lead to a fringe shift or a beat frequency in the equipment when it's in uniform translational motion. The special theory of relativity does not apply to the Sagnac because the Lorentz transformations are restricted to pure translational. He's going on to describe the thing that Tapioca and I discussed earlier about how, if you just use an integral, well, you can do it anyway. But what he's saying here is, while the situation is saved from the formal contradiction, it did leave for the disturbing conceptual discontinuity. And why did the Galilean kinematic suffice for rotational motion but fail for pure translational? So again, if you invoke the frame of Lorentz symmetry with an observer at the center of the device and an observer at the rim, doing the motion, well, both theories predicts that they're in relative motion and uniform motion to one another, and there should be no fringe, right? And he just said it out loud in 1960. So shout out to your boy, because if you're going to be consistent with not having absolute space to preserve the path length change that clearly the measurement is made with, made against, you would have to predict that there's no fringe. All right. So we're looking at Einstein clock synchronization based on the constancy. Earlier, we looked at the half timing corrections and the half timing corrections for the one-way speed and how it would be proportional. So clock synchronization was actually based off of that. When they're like, okay, well, the one-way speed must be the same. So they assumed that based off of that, they could apply a half timing correction when a moving clock intersects with a stationary clock. So we'll read through the process here. So assume that the speed of light is c and is constant for the both one-way and two-way trips. Okay. 2, when the moving clock alpha intersects with the stationary clock A, the signal is sent from beta, encoding its alpha's start time. Then the moving clock beta receives the signal and applies the half timing correction to account for the time travel for the speed of light. Number 4, the moving clock and the stationary clock B are then synchronized, and their times with A are corrected using that half timing correction signal. And then any difference between the moving and stationary clock is adjusted to match the stationary clock. So there's one final thing they can do that was put forward by, I think this one was Jace J. Let's go with them, the Tokyo one. So they had the clock from, Washington to Tokyo, and then it was out of sync, proportional to the velocity of the craft that was carrying it. And they sent one final half timing correction, or not half timing. They sent one final quote unquote Sagnac correction to offset it, to put it in sync. So, they had the predictions for the clock synchronization protocol based on relativity theory, based on Einstein's predictions. And as they were building the GPS system, they were experimentally figuring out that these clocks did not stay in sync in accordance with relativity theory. So that's what we're looking at here. And that's why these clocks require corrections when they're in relative motion against, the ECI reference frame absolute ball or whatever, where there's nothing to be relative to. And then here we have Neil Ashby kind of laying out the specifics on the GPS, right? Because maybe I'm wrong. Maybe a satellite is an inertial system or whatever, right? Well, this is Neil Ashby saying the Sagnac effect on the global positioning system. All right. He says that it is defined as a local inertial frame. So this a satellite in free fall around us is in a local inertial frame, and it should not be accounting for its velocity 1-to-1 as it free falls around a ball. And then here we have our boy saying observers in the non-rotating ECI inertial frame would not see a Sagnac effect. Instead, they would see that the receivers are moving while the signal is propagating. All right, so great. So no Sagnac correction then, right? If you're on the surface of the Earth? Oh no, they argue that. So from this point here, Neil Ashby has conceded my point, right? The only way you could get out of this is through sophistry. This is the whole issue right here. Observers in the non-rotating frame. So if you were to invoke the center of the device, the center of the Earth, or what have you, right, you would not see the Sagnac effect. And if you were in uniform transitory motion relative to that center point, right, so if you're on the rotating ball at that fixed speed, because the ball only has one rotational speed, if you're on a uniformly rotating, or if the device is rotating uniformly relative to your fixed position at the center of it, right, same situation, you would not see the Sagnac effect. You would see the signal, you would see the receivers moving while C is propagating at C. So to say that GPS accounts for the Sagnac effect versus a Sagnac correction are two different things. That's why when A.G. Kelly was writing to GPS lads who were in charge of the clock synchronization standards, he was like, hey, how come you guys are Lorentz rotating instead of Lorentz boosting? That doesn't make any sense. So that's why they were like, yeah, you're absolutely right, dog. Anyway, catch us later. So that's how they wrap that up. And this is Neil Ashby. This is the GPS fixer. This is the guy that after I think they call it the Around the World Sagnac Correction Experiment or something experiment in GPS, this guy went on like a 20-year tour telling everybody that Sagnac correction is in GPS. It works with relativity. This is where all this comes from. This is the source of it. So this quote unquote effect that's trying to be explained through relativity shouldn't even produce a thing that would require a correction. All right, Neil, sounds super coherent. I hope people dig into him trying to explain this, because it can't be done without sophistry. All right, so moving on now, we have Professor Carol Alley from the University 7, and we'll read his quote. He said, I think it is appropriate to realize the first practical application of Einstein's ideas in actual engineering situations are with us, and the fact that the clocks are now so stable that one must account for the small effects of the variety of the systems that we are now undergoing development and are actually used to compare timing worldwide. It is no longer a matter of scientific interest in scientific application, but it has moved into the realm of engineering. All right, one second. Check this. So, let's see here. So he's saying that all this abstract math that they do to explain things in the sky and whatnot, right? They're bringing it into engineering now. We're in how that panned out. So we're going to time travel to 1995, and we're going to see how relativity and GPS is working out. So this is GPS and relativity and engineering overview from the boys at the GPS Joint Program Office. So these guys are in charge of explaining to the engineers that the government has hired to improve the accuracy of GPS, why the corrections that would facilitate the increased accuracy, through relativistic corrections, aren't implemented in the system. So we will give an explanation detailed in the formulas of the relativistic corrections to be implemented in the high-speed craft, in satellites, and et cetera, when using the GPS system, and also going from satellite to satellite. So one of the operational control systems of the GPS does not include the rigorous transformations between coordinate systems that the general theory of relativity would require. The transformations to and from the individual space vehicles, the SVs, and the monitor stations, the MSs, are usually on the surface of the rotating Earth, and the geocentric Earth-centered inertial frame, the ECI, in which the SV orbits are calculated. There's a very good reason for this admission. The effects of relativity, were they different from the effects predicted by the classical mechanics of the electromagnetic theory, are too small to matter, less than 1 centimeter for those on the surface near the Earth. However, a new class of users who employ satellites that obtain the time and position of the position in space from GPS cannot be satisfied with the approximation of the current operational control systems that they have, so the current guidelines they have. Furthermore, the approximations, or because of those approximations, have not been publicly analyzed. This has presented much confusion about the GPS in the literature, right? So what he's saying here, and he goes on in the paper to show, like, hey, the effect of the gravitational potential versus the velocity correction that we apply for the rotation essentially cancel out. We don't need to correct for it to make these clocks or any more accurate, or to make these signal to receiver any more accurate. Nothing like that. It just kind of just works out right now. So in 1970, homie's like, yo, we got that relativity, boys. It's real. We're putting it in the clocks. 1995, no clocks. And then same guy down here at the bottom, Carol Alley, one of the engineers on GPS, writes in, and he said, and that if one perhaps does the explicit recognition of the special relativistic effects, I mean, it took a long time to get the general theory down, or properly down, but I think that it's more or less correct now. But its absence of any explicit acknowledgement of the special relativistic effects due to the speed of light being the same whenever measured by an observer, leading to the relativity of simultaneity and the associated Lorentz transformation physics, there's nothing of that modeled in the current system, and I think there should be. Thank you. So this is a devastating blow to relativity theory, and on multiple levels. And we'll start with the principle of relativity of simultaneity. So all the way back to the first postulate of relativity theory is that there's the principle of relativity of simultaneity, which is that due to the constancy of the speed of light, simultaneous events will be out of sync for observers in motion relative to stationary lads. And now we covered the example earlier with, in reality, if it was dependent on a bomb going off, well, the bomb would go off every time, regardless of the relative motions of the observers observing the signal propagating to the bomb. But anyway, they've, wrapped up this idea and the mysticism of all that. So in other words, what can be said is that there's no cohesive timeline of events, right? Everything's relative to velocity. So you can only figure out how much you're deviating from some event based on your velocity and another observer. Now, GPS explicitly functions in the face of that. So if an observers are on train cars, stationary observers all the time, they intersect, all the time. Everyone gets their signals. Everyone gets their distances derived accurately. Nobody requires additional corrections for the relative motion to one another to establish a cohesive timeline, because it would be like essentially a never-ending cascade of approximations to try and make it work, because there's no cohesive timeline for these events to be in synchronous with, right? So GPS, being that timing measurement system, it has a cohesive timeline that's kept by the clocks. So when the clocks are sending out signals for people to get their distances based off of, they're all synced to GPS time, which is maintaining sidereal time down to 9,196 millionths of a second. And that's all facilitated by explicitly not accounting for relativity in any meaningful way. And then from that, right? Even syncing a cohesive timeline like that shouldn't be possible. But so they got that done. Now they're making measurements for observers in different states of velocity based off of that timeline, and everything is working out without any Lorentz transformation, boys. No link contraction, no time dilation, no constancy of C. Right? Because the relativistic physics here, the Lorentz transformation, is about facilitating the constancy of C. So It's devastating. I mean, it's just like, it would be like the equivalent would be, you know, it'd be cool as if the Bible had anything in it about. I keep hearing about this Jesus character being a constant influence in the Bible, and he's not in there, right? Like if you read the Bible and all, like you just like there just was no Jesus in there, or like you were told like a brief mention at the beginning, hey, there's this dope character named Jesus, you'll learn a lot about him, and then he's just not in there. Like that would kind of be the equivalent, right? Like the fundamental core of the thing that you believe in isn't incorporated in technology that it would explicitly have to be accounted for, right? As noted by the excitement by Homie in 1997, when he kind of jumped the shark a little bit by announcing that it's no longer just, you know, a theory, and it requires to be accounted for in engineering. So we now are going to look at the raw timing corrections from the lads that went to see if the speed of light is isotropic or anisotropic. So they examined some raw timing signals, and they've from a GPS, what is it, station in Colorado, I believe. And anyway, the data was already corrected for the Sagnac effect, and they misappropriate it and call it a second order Doppler shift. And you know, that's obviously not what it is. But the fact that it's already corrected for that right on the raw timing shows that because of that offset, like you're not going to be able to use GPS to find discrepancies in the globe, right? Because, you know, we're big into, why do these distances match? Why is it all proportional? Well, this would facilitate that. So here we have an analysis by Daniel Garzi, who's going over the Wolf and Pettit's mistake here. He says, Wolf and Pettit, 1997, tested the isotropy of the one-way speed of light by analyzing the GPS satellite of the timing signal database and found no discrepancy on the source receiver in motion, which they interpreted as evidence that the speed of light was isotropic. However, Wolf and Pettit noted that the data set that they analyzed had already been pre-processed and corrected for the Sagnac effect, in this case, a first-order change in the time of flight of radio signals between satellite and receiver. So this is direct line of sight propagation. And they justified the correction by claiming that the Sagnac effect was a relativistic effect in the second order in C, which is not true, right? We went through the proportionality of the measurements of the ratio to the velocity versus what relativity is able to predict with the square of the velocity over the speed of light. So, and therefore, that the correction had negligible consequences in their analysis. But this correction was in the first order of the velocity component in the line of sight between each satellite and the ground receiver in the ECEF frame. Oh no! Thus, while the effect of the first order line of sight velocity component in GPS is clearly evident that the raw timing signal data, this first order component had been removed from the data set that Wolf and Pettit used to show that the speed of light was anisotropic. So that's, you know, again, just showing that even like, oh, dude, where's your Nobel Prize? Like these guys literally looked first order timing corrections and was like, nope, speed of light's constant. You know, it's like, did they do that on purpose? Was there malicious intent? I mean, who knows, man? If you're just looking at it and you're like, I don't know, man. With all the conflicting narratives, like you don't even have to attribute malice to it. It's just they expected, you know, that value and they got it. So now we're going to look at the midnight noon redshift problem. So in the 70s, it was pointed out that there should be atomic clock corrections for midnight noon redshift. And what this means, smaller. What this means is that a clock on the Earth when noon is facing the sun, so it's going to be closer to the Earth. And then on the other side of the Earth, about 6,000 or 7,000 miles on the other side, it's at midnight. It's going to be at a different gravitational potential relative to the sun, right? So the sun's gravitational field, being responsible for all the bodies and all that stuff, and the Earth moving through it. Well, that density gradient is going to change not only daily, but throughout the year as we get closer and further away from the sun. Because remember, on our orbits, when we're perihelion and aphelion, we're about, I think it's 3,000 or 5,000 miles closer or thereabouts. 3 million to 5 million miles closer. So that's, largely going to affect the gradient, not just daily, but annually. And none of these corrections are made. So the guy that put forward this hypothesis, right, and showed his math and mathed it all out was was found to have not, derived it correctly. So that guy Neil Ashby that we talked about earlier made the corrections to it, and he basically essentially what he did was he nulled it out and said that it'd be offset by blah 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 blah, right? And he was going to publish this in some journal, and Ron Hatch got wind of this and was looking into these corrections as well, and he noticed that the dude in the 70s did it wrong, but also what's his name? What Neil was putting forward was also wrong. So Ron mapped it out and gave the proper corrections for it, and predicted that there should be an amount to be corrected for, and they were going to have their things published, or Ron was going to have his refutation published at the same time and in the same journal as the one that Neil was having his gravitational analysis posted in. And Neil wanted Ron's refutation to be pulled from the paper and to be put in a separate issue. He wanted his to be published uncontested, and the editor wouldn't agree to it. So Neil pulled his paper from the publication and published it at another place, to avoid that criticism from Ron. So again, I'm not a math lad. If these guys get into a math fight, it's anyone's guess who wins. But if someone's that afraid that they, remove their publication and take it somewhere else and don't address the guy directly, right? Because he never even addressed what Ron put forward, right? So he just straight ghosted it and put it out there. So I'm going to go ahead and say that one of these led correct prediction and the other one didn't. So anyway, this visualization here is just to illustrate the issue at hand here, is that if all these dynamics of the solar system as applied to us through the theories of Newton and Einstein were correct, there would be external forces, or external corrections that we'd have to make that would be coming in, from the sun and its gravitational potential and all that. All right. And I think that pretty much wraps up the presentation.
Wait, did you put the gradient on? I didn't see it. Is that the gradient? Oh, it's on. It's on. I see it.
I just left it on. I was too lazy.
Okay. Right.
It's permanently on. Hold on. I'm flipping it off now.
Yeah, I can. Okay.
Oh, no.
All right.
God,
we're all
dead. We're all dead. The sun just ate us. All right. We're back.
So
right,
what you're saying is there's a bunch of corrections that you would say would be necessary if the other corrections basis that they were making was true, then it would apply here, but it's not in reality. Is that what you're saying?
Yes. If everything gave a cohesive, meaningful, dynamic explanation system in the cosmos, these effects that, are supposed to be producing the motion of these bodies and the retardation of clocks and etc. would be, would be completely applicable. And the fact that they don't use them implies that, there's several implications here, right? There's that the Earth is stationary and that the effects that they're accounting for are not in relation to how they've been presented to us, right? So when they took, the concept of applying Newtonian dynamics to Kepler's laws to saying that the cause that the actual cause of the motion, right, not just mapping a periodicity to the event and then saying that that's proportional to some sort of distance of the semi-major axis of the orbit, right? But to give like a physical explanation as to why these bodies move, they started applying Newtonian dynamics, right? So mass attracting mass is going to produce a velocity of 30 kilometers a second mandatory, right? Like, so that's where all these predictions came from. This is why they were looking for a specific amount in Michelson-Morley. This is why all this was significant, because when they started realizing that they could measure translational motion, they were like, oh, boys, our cosmology is entirely based on translational motion. Let's see if we're moving. And then they didn't get a velocity that would be proportional to their belief system, right? The implication that you could read it is, so if you take the measurements at the first order, right, no Lorentz transformations or assumptions, you would have to say that the Earth is moving way slower, and to compensate for that, and using scale invariance, you would have to move everything closer to maintain a belief system that the first order measurement of the velocity of that you believe in is facilitated by covering a different distance than what's put forward in the heliocentric model of 93 million miles. And then another interpretation would be that the Earth is stationary and that there's an ether wind that goes from east to west or west to east. Any questions, comments, or concerns?
So this whole thing that they've been using as proof is actually one of the absolute worst proofs against their model.
It's so devastating that not only does it, I mean, it underlines general relativity, special relativity, like the two of the three pillars of mainstream physics. So general, special, and quantum field or quantum electrodynamics. Just completely cuts them out in terms of ways to explain why there's no motion that's measured, and yeah, and like removing the ether as a material substance, right? That all motion's relative to, and all that. Like it changes everything, and they turn, and so to remove that fact and like make it, promote their worldview, they had to they tell everyone that GPS is of their theories, right? It's like Winston said, it's always the inverse, man. The thing that falsifies their theory the hardest is like the thing that they'll invert and say gives the best proof.
But who's surprised by that? Are you surprised by that? Like,
At
it's like
the-
the thing that's
at
their
this
best
point,
proof. It's like, does it not only does it not support them at all, counterpoint supports our position. Oh, how does that happen every time? Oh, because when you just lie about the things that disprove you and soup them up as evidence, then I guess there's a chance people find out.
yeah, that's
Crazy.
and then like all it takes to get the engineers on the ground who stuff, you just give them a little story. Like, oh
And
yeah,
then,
dog, we'll get you on that correction on the flip.
like that dude, or not like that dude, like I think Daza did a good job of demonstrating. I mean, all you need is to present someone a framework of data. Like you can have a tech or a person or a satellite engineer or anyone, give them a framework or a geographic gratitude to work with. Here's some XY coordinates. Do your work in them, compute your answer, return me some XY coordinates. Okay, here you go, all done. Why would they ever look out of that framework of the coordinate system they're in to be like, oh, is there perhaps another relevant covariant system that could be processing at the same? Do I live in Cartesian simultaneity? Like, no, he would never even think to ask that. So of course it'd be easy. It'd be easy to trick everyone that way.
That was an awesome presentation, Alan. I should prepare some content in case your internet goes out so I can entertain the flock next time.
So it's actually as part of the janitorial need that someday at any point for any reason we may call upon you to do a presentation and you'll have to do one like on demand on any topic. So just be prepared.
Yeah, there's a story that Einstein's chauffeur had heard his presentation so many times that one day Einstein wasn't feeling well or something like that, and then the butler gave it or something. Just fully recited it. So that's you now, janitor. So
Yeah, I'm on that
learn
level.
accordingly.
Listen, I'm usually in bed by 8. It's 2 a.m., but I wanted to stay up and finish it this time. This is a very similar presentation to the other one that I saw from you.
Identical, even with some
Yeah, it
additives.
was almost the same.
It's very similar, I want to say. Give my finger on it.
Definitely had the same sentiment.
Now, I noticed one of your notes. Hang on, let me link it to you what I'm referring to. One of your notes here. All right, reply at Alan. So one of your notes mentions whether or not the concept of RZA is real. Now, are you referring to the Wu-Tang Clan member?
Reciprocal zennies. Oh.
Wu-Tang Clan ain't none. I'm actually referring to the RZA, the GZA, ODB. Yeah, dude.
The reciprocal zen.
No, those are reciprocal zeddies, right? So the whole reason about geodetic surveying and the relationship there being that they're saying that the gravitational potential is so offset that it's physically deviating their plumb bob from their expected, straight down to the center of the globe, such that they have to physically tilt their device to compensate for it.
Why would you have to tilt the device?
Well, if your coordinate system isn't in alignment with the stars, but you need the ground to be comported to it so that you can tell people that when they use your coordinate system, that the globe is the truth.
Oh, cheating.
Forever and
Got it.
always, yeah. Forever and always the truth. Don't you worry.
Got it. Got it.
But dude, even people like our boy Eric, right? Like who
Oh,
would just be given data or a framework of interpretation, given some, intellectually challenging or stimulating work to do within that framework of interpretation. He does said computations or adjustments or whatever, goes home, would never know, oh, well, what do you know that the Earth actually that you live in isn't this spherical coordinate system that you're plotting XYZ and all day? Like, no, would never occur to him. And this is the damage they do with this whole, I guess it's like a trifecta layer of just stuffing and crap and like powdered sugar that they dump over the turd of relativity to make people like think that it's simultaneously the best, most predictive theory of all time, but also a complete dog shit, never predicted a thing in all of history. Like, oh, the hell of a complicated
Well,
history.
yeah, it's a bit of a mess out there. But yeah,
Hey,
we dissect and go through it.
about Jupiter's cock. What are y'all talking about?
What's that, Meow?
Jupiter's cock. What are you guys talking about?
Well, we're all geostatus. We just prove without a shadow of a doubt the Earth's not in motion based on high level interferometry and a whole bunch of relativistic effects applied to atomic cesiums and relativistic things that actually aren't time dilation and all the various effects of relativity. Y'all caught up?
Dude, where did my boy Tapioca go?
Yeah, I was gonna say Tapioca really contributed to the stream. I
Oh,
was
dude, I
super
know that
happy
was
about
so
that.
awesome. He
I
came
love
through.
the powdered sugar over the that's freaking hilarious. Holy crap.
Oh, is
It's a good
that
analogy.
paraplegic bear?
I was gonna say, is
Hey.
that paraplegic from Paraplegic Coffee? A rival coffee?
Oh, do
God,
you?
what do you call him? Cartel
Ooh,
Lord?
Hey, eat it.
dude, he's definitely got baby penguin beaks in his. I'm just saying, but nice to meet
Oh, dude. I mean, I'm not trying to spread any rumors, but I've.
That's awesome, man. I never met paraplegic bear until today in Discord chat. All I knew of his lore was from Mountain Bear clips and random Owen references.
The man, the myth, the legend is upon us.
That's awesome, man.
Dude, I love how the links between the geopotential like requirement for a geoid, the geodetic surveying, the reciprocals that like even leveling through satellites and stuff that all of that ties into just trying to like hide the globe via the unfalsifiable bubble wrap of say relativity. It's like, yeah, so we're gonna use this equipotential. It affects plumb bobs, but not clocks. It pulls strings, but not the planet. Sure, we're in one gravity well, but the sun, which pulls everything around, and equipotential free fall would be a mathematical amount. That doesn't affect anything, but it affects everything all at once. And in between this web of nothing of interconnected nonsense, we're gonna have this effect, which actually only needs to go one way. And dude, I can't believe in all honesty that anyone believes it, but it's because nobody understands it.
When you a hidden camera with the guys that are like tilt the thing. Come on, man. We gotta make it look real. You know?
That's exactly it.
They'd be like, I don't know. Somebody's gotta come out and just be like, all right, I am sick of tilting things and just completely just sugarcoating stuff. That's a hilarious the analogy about powdered sugar and this turd of whatever the hell relativity, whatever the hell you said. Such a damn shame.
You know, when you have like
Damn
a
shame.
when you have like a really shitty theory, but you need and want everyone to love, buy, and authorize it. So like it's a turd, so you just get a whole bunch of powdered sugar and you dump it all over the turd, and you hope that people don't notice it, and you try to pass it off. Right? That's what relativity is in a nutshell. So that's the bubble wrap on the turd of the globe.
It certainly has lent itself to a lot of, like where it's like, oh, we'll just explain this phenomenon as relativity. Like, all right,
it's the
are you sure?
catch-all.
Are you sure you want to attribute Thomas precession to it? Because it's going to conflict with Michelson Morley, Michelson Gray Pearson. They're like, nah, I don't care.
Nah,
You
it doesn't
guys will
matter.
forget about it.
No one will even ask us questions, bro. Don't even worry about it.
Dude, it got to the point where Homie was trying to invoke absolute space with respect to different fields all tethered to that space that would be in rotation.
Yeah, so if you were to explain something like that to the layman, not in scientific lingo, to any soccer mom or person in the world, and they were like, "This is what you believe to maintain that you're actually spinning through space, rocketing around the sun," they'd be like, "That's retarded." Right? So what they do is they put it in scientific lingo and formulas so that it sounds like elevated speech wise, like they just like it's like you know how you love that term like superfluous verbosity as it applies to like special elevated language. You could do that, but for math, and people are like, oh, I don't get it, but like clearly that's important, and that's obviously it's right, and that's what it is, dude. They're like, bro, so to get out of explaining to with like words where people would laugh at them. They're like, okay, here's what we're gonna do. We're gonna invent a new branch of physics. We're gonna describe it with these fancy formulas. I got this tensor. You got this tensor over here. You see that equation? You see how it's conforming to the superfluous bending of space time? Yeah, you're too dumb to understand. Sit down. I got this. Daddy's home. Einstein.
Daddy's home. Sit down.
Like we can't make the Earth move. Whatever should we do? Hold on. Who are you gonna call? Well, listen, I can't make it move, but I can make some math that will invert the reference frame around the thing that won't move and put you in its center so that to you, it appears that it's moving, right? How would that do? And they're like, whoa, Einstein, the Earth mover. He really did it. He made it happen. The Earth totally moves.
Yep. And then, so I think so to end on, does anyone any other questions? The screen share thing. Anything else?
I don't have a question, more of a critique. Could we have more pictures next time?
No.
You don't like how Alan's presentations are all screenshots of PDFs and papers?
I just like pictures. Those are the books I prefer to read.
All right. I'll give you, bro. Look at these graphics.
Whoa.
Do you want to see a gradient real quick? Hold on. We're gonna get the
Could you
special
show
effects
me the
team on here.
time space warping one again? That was my favorite one.
This is a special ether cause custom job here for the gradient density spectral matrix, and it's actually a visual acuity of a certain degree being displayed. Yeah. There you go.
Yeah, so what we have here is the offset of the equigravitational potential of the sun relative to the Earth as its annual motion around it. And because we know that the heliocentric model was correct, because Kepler looked at the sky, and then other people looked at the sky as well, and applied Newton's equations, which, the mass cancels out, and it's all based on a ratio of constants established anyways in relation to the periodicity to explain it, so you wouldn't know the difference anyway.
Dude,
But
that's
anyway,
literally the way people got brainwashed over the last freaking 40 years, dude. Listening to idiots drone on just like that.
Agreed.
With some fancy bullshit. Is there enough actual surveyors that could kind of get together and be like, this is what we're doing, and it's not matching these other doofuses that don't really.
Oh, they do that every day. Yeah, they do that every day. The ones that don't match, they just throw out.
So, and I know a lot of them are flat earthers. They have to be, or they're figuring out, that it's definitely not obviously clearly. Quite a few CAD drafters too. I was a CAD drafter for about 8 years, so kind of painfully obvious. But I don't know. I guess you just sit in your little bubble and believe the crap, and believe they're bouncing signals off of crap and getting it back. I guess maybe you just stay asleep.
I don't know. Kind of mumbling off there. Didn't really hear what you said. Kind of trailed off.
I don't have I got a crappy Bluetooth in, so I apologize.
All good.
Well, that was great.
Oh.
Thanks, Alan.
Yep, no worries, lads.
You must be tired because we had a long day of rating Red's rhetoric and then preparing for this or whatever.
I mean, you guys did. I was just fucking throwing
Oh.
heels.
Oh yeah, I forgot you were there, but he didn't let you in. You feel like you were there because you did all the work, you were prepared, but he was like, nah, if I don't acknowledge you, you don't exist.
All I'm saying is when the boys are ready to go to war, like, you know, your boy's showing up. So
that is comforting because I did think I was alone. Turned around, you weren't there. I was like, what the fuck? He's being held back. He's in the other room. It's okay.
Yeah, if somebody recorded that presentation, man, I would love to get it on my channel.
It
I
should be.
I got one of the first ones you did.
Yeah, so half of it is on my channel because I DC'd in the middle of it, but the full episode should be on Earth Awakenings. There's a brief interruption where I DC'd, but it should be on today's current episode.
Yeah, I think I'm gonna screen cap that tomorrow while I'm at work, if it's okay.
Oh, dude, absolutely, dude. Share it. Fucking do whatever you want with it, bro.
When you say screen cap, you're just not going to download it and upload it? Why don't you just do that?
Yeah, just so you guys know for future reference, everything I do is under Creative Commons. You're free to use anything I use or make in any way.
Yeah, so I can do it at work. I don't know how else to do it. You said download it, then I would have to edit it. If I just screen cap it and then pause it, and then when he comes back, start recording again.
Well, I can. I can cut out this part of the live stream and post it as its own video as well. Just the entire cut from when it starts, until the end. If that's what. Are you wanting the one from here where it shows the whole thing? Because yeah, Alan's. You're saying Alan, yours will have most of it except for the cutout part. So yeah, you could cut it from there as well, or just listen to it on your channel.
I don't think I have a YouTube channel.
Yeah, so basically it's on Alan's channel. It's already, other than the little part where he dropped out, but most of that was just us talking about other topic anyway. So
no, the entire other half of it, I didn't go because I was afraid it would mess with the bandwidth. I just wanted to finish it on here.
It probably was.
Oh, I see what you mean. The second half cut. Okay.
You were streaming too and doing it in here, and it's too much, or what? What happened?
No, it's not. It was my internet had some issue. It was like an outage or something. I had to reset the thing.
You have a lot of outages, bro.
Bruh, don't judge me.
It's like
a relative convenient.
A relative outage ratio is like very largely your way. I have 0 outages. I don't know what's going on.
Kind of coincidental, kind of convenient that the outage.
Always when we need you to be there.
Also, I noticed that Levelist left the
Disappeared.
channel.
I knew it. I knew you were gonna say that. I knew someone was gonna be like, dude, Levelist just gave the best presentation. You over at Geos.
Dude, sometimes I'm like, I don't remember saying, oh, that's Levelist talking. It's not me.
Same happened with Ruhif and Dazzle, dude. It blew me away, but then because I almost called him Ruhif, everyone in the comments just decided that he was Ruhif, so they would like critiquing Ruhif on Dazzle's responses.
Dude, when that girl called Ruhif English and did a mock English accent, I fucking lost it.
Yeah, I think that was besmirched by Ruhif calling her a drunk and her immediately like lashing out. I was like, oh no, she is then, I guess.
That's what made it. That's what made it especially funny because of the visceral reaction. Like, when you cut someone to the core.
Yes.
Like
that's what Ruhif did, though. Yes.
Yeah, he diced her to the core, and like I was like, damn, that's embarrassing.
Yeah, because of her reaction, I was like, ooh, nailed it. Ooh.
Yes, I know, because of your reaction.
Damn.
We all know.
Yeah, like it would have been fine if you ignored him completely, but he called you he premeditated on it. Was like, I'm gonna get her on the way out. He's like, all right, boys, it's been fun, and you're drunk. I'm out. And she was like, oh. But she was cool. She immediately was like, you're an asshole. You want a peer-reviewed paper to have an opinion? You fucking
the coolest drunk lady ever. Usually they're the worst. She's super acceptable.
She said she was a radar tech in the Navy, I think.
Dude, that's what's up. We'll have to get her to talk to young Pizio about some radar reflections. Dude, Liliana, did I see your mic lighting up? Were you about to chime in for the first time on EA?
Wow.
Oh, can you hear me?
Yes.
Yeah. Well, I was just going to say it's a brilliant presentation. Thank you so much for sharing. And I was just going to say, how do we get more whistleblowers to come out and talk about stuff like this? Because there's got to be people knowing about this deception.
I found the best way to do it is to wait until they retire and then email them and go, hey, you know that thing you did for about 30 to 50, 60 years or so? You didn't happen to notice anything wrong with it, did you?
Yeah, it turns out you have to wait for them not to have a financial vested interest in supporting their kids' family and life for them to want to go against the system. And actually, when they retire and they've taken that away anyway, is the perfect time for people to go, screw them. I will tell the truth. It seems to happen then, mostly.
Maybe if they could maintain their anonymity or something.
Yeah, maybe. That's what I was gonna say. Like, not to mention that once they do reveal, people in not just in this chat, but people in general on the internet will make it their life's mission to destroy their career, destroy their family, like get their kids taken away, do anything they can to destroy their life if they dare to come out about Flat Earth and be public. So that's probably a large deterrent, in my opinion.
Yeah, I guess it's, we'll just have to keep spreading the word somehow.
It's like they have nothing to gain, right, from being truthful about Flat Earth if they know it, and everything to lose. So you don't see very many.
Yeah, it's so sad that so much is being controlled through money.
Yes.
Yeah. Well, for example, Ruyang Wang, who won't publicly speak out against relativity theory, although he's published papers that, go in the face of it. And the most recent one, I think, was 2022, where he showed a bunch of fiber optic gyro configurations in conjunction with atomic clocks that would help you determine the flight path around the circuit to see if the speed, to verify the correctness of relativity theory. And even though he's done those, right, he won't present or speak publicly against it, even though he's experimentally falsified it, patented technology based on it. Other corporations have patented a similar technology that, based on the same principles that Wang's, patented his on, which he found in his 2004 experiment, and, et cetera, et cetera. And it just goes on. And it's like, how come we don't have that linear interferometer to measure, or, to provide this technology? And it's like, well, it would the implications are insane. It would falsify everything in regards to the mainstream paradigm. It's contrary to everything that they've put forward in the last 100 or so years of physics. So they'll never go back on it. Like, it's going to be up to us to withstand social shame until all those people die, and then we could tell people that the new thing is just the thing it's always been.
That's what it is, right? That's what they did.
Yep. Yeah, just that's essentially it. So good luck in the battle for the next generation, boys.
Like, screw the adults. They're lost causes. Their sheeple are gone. Their minds are melted. But their minds are gravy. But the kids, bring them to kids' community, the schools, bring them to textbooks. I think we can make progress here, boys.
Absolutely, dude. It's already crazy, dude. So Vandegraff, young lad, and through his academic come up, he's learned that relativity is rotation. Or, I mean, that you could apply special relativity to a rotating frame. Multiple ways to do it. Even he listed, which were awesome. It's like when the relativists that I'm speaking to, or that I spoke to prior to him saying that, have all said the same thing. And they got that older education where it's like the narrative was, oh no, rotating frame, can't use it. Don't, blah, 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 blah. Just no actual answer for it, but somehow saying that it's still an effective relativity. So yeah, I mean, bros, we're this close to putting that absolute reference frame back on the Earth.
Do you guys remember when Dave Weiss was telling us that children's books are in high demand and that he could sell them? I think that we should really take that seriously. Is there any way you guys can dumb things down for a child to understand what you guys are saying? Because actually, I would need that for myself.
Yeah, I'll start tomorrow.
Are you serious?
Yeah.
If you say it, Madam Ambassador, like that's how the hierarchy works. So
No, I'm totally serious. You guys need to do like children's version, and I'm telling you, it would be very useful even for lay people, adults like us who don't
All
know
right,
anything
all
about
right.
physics.
Gather into the story of Goldis and Morley. And
okay, it could be done tomorrow. It is. Let's do it. I see what you did there.
You know, Dave said he'd sell them. He said it's in high demand.
So the first time they tried to measure the velocity of the Earth, the velocity wasn't quite right.
It wasn't there. They couldn't find it. But the next time, it still wasn't there, boys. So they got their step. They tried real hard. Yeah.
Look, you know what? The president just sent me a message and said that he would read it.
Nice.
Well, that sells it. We got to do it.
I mean, we're literally writing the material. So anyway, the third measurement, wasn't quite right, but then Michelson Gale Pearson came along, and then that was just right, but only for rotation. I think there's something that could be done there, Lily. I think you're right.
I'm being totally serious, guys.
I am too. If you think if you think I'm not going to rewrite Green Eggs and Ham about an interferometer, you're mistaken.
The time stretched and it stretched.
And they took the measurement on a boat with a goat and a mouse with a house. Still, there was an anisotropy measure.
That's actually really good.
Oh yeah, you could totally do one like for kindergartners, but then also do something for teenagers, and so you could promote it on TikTok.
Dude, the tale of the three interferometers, right? Mickelson's adventure. Fizeau's exploration, dude. The youngest and most adventurous. Loved the star.
Dude, Lily's right. No, Lily's right. I'm making a children's book on interferometry.
No, I'm not doing it. I'm saying like I've already started doing it immediately, actually. But
I'm already envisioning it in my head. That's a great idea.
I'm totally serious. But then also look, if you make one for teenagers, you just have to make like sexy looking girls and boys, and boom, the teenagers will eat it up.
Well, how about a sexy interferometer instead? Right.
Einstein's already got the hair to match the big bad wolf. You could make Einstein the big bad wolf.
Oh yeah.
Miss Dare, you have to write lyrics for songs for all this.
Children's songs.
Is that the Ether Bard?
I sent the new title and a new tag.
Oh yeah,
Ether Bard. It's the Ether Bard.
I like it.
What if it's an idea, guys, right? Like, and I'm not sure about whether or not I like the sneakiness of this, but if you started a channel that was something to the effect of like a university cheat sheet, this notion that you can sort of, to anyone who's learning this sort of stuff, so, you can, everything you just did there is basically, if you just subtract a couple of your more controversial aspects, you're basically explaining how GPS works. And so you put that all at the front of the video, and you could do this with, I know you guys are pretty familiar with a lot of different sort of forms of sort of how the science is, like relativity and all that jazz. Or dark matter. You could explain dark matter and then, sort of sell it or prescribe it as a cheat sheet, like quick learn this in YouTube videos. And then just be very subtle at the end of it and say something to the effect of, but this is what they won't teach you. This is what they won't show you. And you don't need to be explicit that you're in flat earth necessarily, or, you can just say, hey, this is where some of the controversy is about the nature of this. And you just very subtly hint at the notion of it. And, like a bit of time, you'll get a bit of followers and all that sort of jazz, I'd say. And I'm just trying to think of where just make yourself available. And if they reach out to you, you can redirect them into your ether cosmology channels, and you can sort of give them the hard line at the end of it. I don't know. What do you reckon?
I have a business proposal for you. You do
What,
that,
you want me to do
maintain
it?
the channel, and I'll help you the content with, so you say it right, or decent enough.
Yeah, well, I mean, it would serve me to learn some of the shit that you guys talk about. I was thinking before, it's like, I know most of the terms, I've heard all the terms that you're throwing around, but I haven't mapped it appropriately. I don't know where to slot the terms in where. And I was thinking about it. It's like, if I just put in the hard yards, like, maybe sort of 5 hours on each little subject or something, I'd probably, henceforth, as soon as I start listening to you, I could like map it into the sort of the construct. I mean, it'd serve me a lot more than just sort of sitting here listening to you sort of diatribe about all these sort of crazy terms that I've got no idea like where they sort of slot in still. Anyway.
Plus, college kids love an accent.
True.
Oh, what you want the Aussie sort of
Dude,
they don't
twang.
even get it,
We need a
dude.
good
They don't
Aussie
even
accent,
care.
man.
Like you'll drop panties and boxers. They don't care. They're college kids. They're like, they've got an accent. Listen to them.
Okay. Yes. Well, I sat here trying to sell you something, and now you've spun it back around at me, boomerang style, eh?
I don't like what you did there. I see it, but I don't like it.
No, Ricksky's idea is good because I think what you have to do is kind of put a little costume on it. You can't be direct and say, "Hey, this is related to flat Earth." You can't reveal everything. You just kind of have to disguise things and lure them with, like his idea is good. Like present it as a cheat sheet, for instance.
I just think it'd be so cool to, like, I mean, you were talking about getting people as children, and it's like, it's almost red pilling them too early. They'll never go into the field. And then, like, the other thing is, like, approaching these people, or it's easier to get them once they've already, closed up their career. They're a bit more open to the alternative. I just think, how are you going to get these people who are, like, just entering into it? Like, I don't know.
We got a man on the
power is.
inside.
Who's that? Mr. Bennett?
Can't reveal his name, but he may or may not be going to university.
We may or may not know his real name and his real location.
He may or may not be telling the lads at uni they're morally insignificant as they're coming up in their young physics careers. So, we'll see what happens.
It'd be so interesting because, I mean, what is it? Like, to get a PhD, you need to sort of convince your professors, and they're usually sort of selected from the class, the better and brighter students or whatnot. And then all you just need to do is just get. I mean, look, at the end of the day, I recognize that it's a glass ceiling and they'll never let it through. But I don't know. It'd be interesting if you could, like, somehow sort of essentially poison the well without them knowing about it, and sort of.
I think we just need to make our own. We need to make our own royal society, starting with that, and then we're good to go. Because that's what they did. All they did was get there first, and then establish constants based off of, and then give us, ratios of those as measurements. And they're like, "Oh, look, everything is just as we described it."
Yeah, man, big old G.
Big G, little G, fucking applying it to the sky. Same thing with the electron. Once they had that unit of measurement established for that consti, they built everything upon that through algebra.
That's crazy.
Do you hear me?
Also got
Globo Damo.
Yeah,
What's up?
hi. Alan,
Dominic,
it's awesome presentation, really awesome presentation. But that thing about children books, that's like amazing. That's exactly what we need to do, because they indoctrinated us as childs, and we believe this bullshit as a kid, but we wouldn't believe it as adults. But if we will be able to like get simple like few pages books to like adults who are like flat earthers and have kids, like it would be like a game changer, I guess. Like it would be amazing. These kids have amazing imagination, and if they would see like these books, and then they would have them before they go to public schools, like these teachers they wouldn't have like anything. They would crash them like at second, third grade, like it would be game changer. I think it's amazing idea. I would do as many kids books as we can do, because it will be game changer, I think.
Well, Dave Weiss literally said that there's a huge demand for it.
I do recall him saying that.
Like something about water physics and something like that, and imagine how they will try to like convince them that water can curve around around a rock. It would be like insane. It would
You don't
be
need. You don't even.
amazing.
So you don't get it. It's always curving, just that out of the edge of where you can't see it anymore, and that's why you don't know. Right? Come on.
But you could have several short books, right? You could have like one that addresses motion, another one that addresses, um, curvature, and like even one that addresses GPS. I mean, there's all these little subjects. You just have like small books, like short books, right?
Yeah, like we should have like this flat earth 1-on-1, like do that in kid book, and it would be like crashing.
Especially
Yeah,
with
we
kid
need
books.
to announce during maybe the next Flat Earth Friday or something to see if there's people that are illustrators or whatever. But it looks like, I don't know, you, Shane and Alan, you guys are so multi-talented. I feel like you guys could do all the illustrations and stuff.
I guess that's why Witsit tries to do everything all the time, huh?
Yeah, dude, I just immediately realized after I just committed to the book thing, I was like, yeah, but I
Yeah,
have
I
the
think
same energy 20 minutes from now.
yeah. Well, yeah, dude. Like he starts like 7 companies. And we're like, yeah, let's do it, and we support him. And then it's like, what happened to that? We just need some follow through. Is all I'm saying.
All right, fine. I'll start page 1.
We're not bad on initiation. Contact is like pretty good, pretty good. Just need some follow through.
I can actually draw pretty well. Just throwing
Nice,
it out there.
nice,
nice.
Need that.
Because you can do AI art for it, like what Zach Zimbala is doing.
Yeah, I was going to
but
do that.
yeah, you can do that. But it might be nice to have some actual
Oh, you're
human
hired.
touch.
Yeah, you're
What's
in.
up?
You're hired.
Yeah, I mean, if you give me the concept of what you wanted, I could definitely draw some things.
Nice.
And make them, kid friendly and stuff. I look at those books all day long because I'm always reading with my little boy, so it really wouldn't be difficult to do.
And I wouldn't even be afraid to do some crowdfunding or something like that, because I think I don't speak even for myself, but I would definitely like support this, like definitely.
Right.
Well, I'll get back to you guys if I fucking start it. Like it's all just.
Yeah, one thing I'll say is that if you're gonna do children's stuff and you're gonna you gotta explain what velocity is, or
No,
use a
dude.
smaller word.
Dude, in the tale of the 3 Michelson interferometers and the children's search for the speed of light, dude. I already have the title. It'll be fine. Whatever.
Searching for the
can I make
velocity
a
of Earth
suggestion,
through the.
guys, real quick?
Absolutely.
Hey, Alan. Hey, Shane. Just want to say what's up, guys. I'm kind of wondering why, your channel and stuff hasn't, took off by now, because you guys have obviously been at this for a while. And I know it's not your guys' fault. You guys are putting out, the best info, doing, the the backbreaking work for us out here, you know, and keeping everybody honest, but it's not reaching everybody. And I'm thinking, I'm just throwing this out there, you know, all the other ideas were great. You know, books, all that. But I mean, the way people are receiving their info anymore is, you know, these clips, videos, whatever, you know, the shorts, YouTube shorts. So maybe it has to go under a like different channel, a total like, you know, IP address, something, you know, that's not flagged by Flat Earth. Because these, you know, these demons, I'm not even going to say demons, but, you know, whoever's flagging this stuff, they're doing a great job. One more thing, I'll keep it short. Thanks for giving me the time. I do appreciate it. But also, even just omitting the word flat Earth or even anything like that, keeping that totally out of it, and just kind of giving like the truth about GPS and giving it like an actual factual like vibe, and letting the people decide, hey, well, is this true? And maybe it'll go viral, who knows? But I think these people are like onto you guys, and just after anything that comes out, like with this info, and maybe they just flag it that quick. I don't know. It's insane. But thanks for giving me the time, and just keep up the good work, guys. You know, we're dead in the water without you guys. Is all I'm saying. So thanks, guys.
Yeah, I agree. These guys are brilliant. Well, I think they're censored like crazy and silenced. And then B, to tell you the truth, this is, you know, what they present is just, it's not, lay people can't understand it. You know, it's just above people's pay grade. No, the lay person doesn't have like a physics background or anything. So, you know,
Yeah, I actually like agree. We are censored like super hard, even in Czech. Like if you have you can't even find if you like watch some of our content and then you go to YouTube search in your own history, you won't find there like this videos. So it's really censored hard. And second thing, I super agree. Like this stuff is like a high school of Peter. Like there's nothing like more precise and more advanced than is this. So I think it's not for everybody.
What degree do you think you'd need to understand flat Earth in the South? Seeing the two models are so different in the South.
What do you guys think? Do you think we're censored, Rui? Do you think flat Earth is censored? Other Globers, do you think flat Earth is censored?
Kind of. Like you're not really. Yeah, you don't get
Yeah,
shown
you're
equally,
suppressed.
but yeah.
Okay, all right, that was easy. You guys admitted right away, right? Well, she admitted right away. Rui was struggling until he saw someone else, I think, capitulate, and then he was like, "Oh, it's cool."
No, he said it.
He did,
I
but
mean, it's
only
not bad.
after
It's
you
not
said
bad
it.
like the C word or the or the what's the other word that you guys use a letter for?
Right.
The N word.
Right.
Yeah, but it's so
That's
it's so suppressed that it ends up just being censorship. Like it's just
probably.
suppressed beyond the range of what, you know, within the balance of everything else, that it's basically just the end result is just complete censorship in terms of being able to reach people the way that if you make some channel about, you know, cat videos, you're going to reach a completely different, you know, spectrum of people than you would. So yeah,
It's so censored, man, that they set up a phony society and then had Obama refer to that phony society to create the laughing stock. So, I mean, that's some pretty up there sort of social coercion, you might say.
We don't have time for a meeting of the Flat Earth Society, all right, buddy?
Like, I don't know if there's any other content on YouTube exactly. For example, where if you search some content about, I don't know, vaccination, or I don't know, World War II, or any other topic, and then you go to your own history, you will find that video there. But if you go to flat Earth videos that are like true flat Earth videos, and then you go to your own history, you won't find them there. So it's like I didn't find any other topic that would be doing this. Only with flat Earth content, which is like major, I guess.
Yeah, I guess whatever they can do to stop the truth from catching on, it seems like that's what they want to do. But the question is, will they even succeed with that? I don't think they will. I think but nonetheless, they seem to be, you know, holding it back to the best of what they can do. Because if they just completely outright censored it, that would be kind of almost put up more of an alert to people. But doing it this way, it's like just kind of the fine line of what they're able to get away with, just to slow it down.
Yeah, compare that with the jibby jab. Like, that's actual censorship, right? You get your channel shut down for that, whereas you don't get your channel shut down for Flat Earth.
This may be off topic.
Wait, why'd they suffer? Why'd they do that to the jibby jab? The fuck?
Oh, it's medical misinformation, you know.
So this may be
People's
off
lives
topic.
are at stake, Alan.
Shit. I wouldn't want anyone to get hurt.
Yeah, you wouldn't want to save anyone's life by telling them not to take a vaccine.
Yeah, can I get in just for a second? I'll be quick. It may be a little bit off topic, but I'll tie it back. I promise. So remember you're told in school that Lee Harvey Oswald killed Kennedy, right? And then you find out later that he was actually an asset, right? And where did he work? At the book suppository, right? So I wonder, if all the book suppositories that go to the children are connected to the CIA and the intelligence groups, because it seems like that connection would be there. So if you guys are going to start printing like children's books, you're basically competing with the CIA.
You mean repository?
I'm so sorry. I'm so
yeah,
sorry.
when you said suppository, I was like, I think that's a book that goes in a different spot.
I think the CIA would be able to infiltrate
I'm
any industry or any business that they needed to get agents into if that was the case. I don't think they would necessarily need to own that industry. But who knows? I don't know.
Yeah, I mean, in terms of like, publishing a book, what that would look like is a PDF. And then that's it.
Yeah, like what you say, yeah, right.
Like the CIA can't stop my PDF.
Like if I hit print on a database tab that is formatted like a book, then that would be a book.
Yes. It is now a book.
But yeah, suppressed but not censored, meaning they have to walk that line of like hardcore, not letting people see us, but at the same time giving the illusion that we're still allowed to be here. Everything's okay and cool. Nothing to see here. Sure, we allow flat Earth. We just don't want anyone to see it or hear about it or get notified about it or see a video or search for it or find a title or get notified when their friends. It's like it's allowed. You just can't see it or find it or hear it or smell it,
Right, which on the outside makes it look like, or the kind of, we hear it all the time, people repeating it, is, oh, well, it's just not very popular. It's just, oh, it peaked years ago and it's just dying. So it's like, that's even though they're doing that level of suppression, they just make it look like, yeah, it's just not a popular topic. It must not, So yeah, that's like the narrative trying to go along with that, which is not the case. It's the case because they're suppressing it is a huge factor of it.
Isn't it like so they're retroactively adjusting the data of the interest as well as gaslighting you about the lack of interest, right? So they're like, yeah, sure, it blew up all at once at one point, but then it died down and no one gives a shit now. Like, look at the data. See the Google things? So, like, after that, when we fixed it, right here's when we fixed it and addressed it, then all the interest died. Like, look at that. It's amazing.
Yeah, I keep seeing references in popular media. So The Boys had a reference to it. And then someone showed the other day that there's a reference to Round Earther or something in the new Deadpool. And there's heaps of other ones that are just popping up all over the place.
The fire department show with the Super Troopers gang, dude. They did it. They did pin it on the dumbest characters, but whatever. It's all in so now when it's in media, it tells you that like it's too powerful thing to ignore. So they have to adjust, and the adjustment's always okay. How do we absorb it and pretend that it was never a threat and that we've always, and that's what they're doing now. Welcome was that the new movie with the moon? We definitely faked the moon landing by recording the moon landing or whatever. That's like the easiest bridge to get you to the bridge to the island that they faked the moon landing, right?
Sure.
You don't think so, Rahoof? Where are you on the moon landing anyway?
Again, what? What do you say?
Where are you on the moon landing?
No good reason to doubt it.
But you think it's a bit sketch, right?
No.
No good reason to doubt it.
Totally legit. Yeah. No reason.
But what is the sketchiness level for you?
Trying to save.
I don't know how else to say it. I don't.
Zero.
There is no good reason.
Zero.
I've not seen a good reason to have any doubt about it.
What about 9/11?
What about 9/11?
Done by a dude in a towel head in a cave.
Dudes
I
planes
I
into
have
buildings.
Yeah. I mean, like, do you buy the official narrative on 9/11? That's what I mean.
That dudes
I
flew
have
planes
something
into
to do with
buildings.
the moon land. I have something for the moon landing, Roofy.
Yeah.
Yeah, I find it a bit suspicious that they took us out of school to go and watch the moon landing in '69 when I was in primary school.
Why? That's a huge, civilization
Big
event.
propaganda. Right? Oh, yeah. What you said.
Hang on, didn't Australia help them get to the moon? Like, didn't they?
No, Parks had nothing to do with the trouble with the big dishes to help relay the communications or anything. No, we didn't have nothing to do with that.
I thought they relayed the TV signal.
I thought it was
Yeah.
just
There's a movie on it called The Dish. If anyone wants to watch it.
Yeah, when I was a kid, they pulled us out of school to go watch the Challenger fake blow up. Well, it did blow up. It did blow up, but it wasn't the story they told us. I mean, there was a thing that exploded, but it didn't have people on it, I don't think.
Or did you go outside and actually watch it on TV?
They pulled in they like pulled TVs into all of our classrooms and made us all watch it.
They managed to do that because they had a teacher on the crew, didn't they?
Oh yeah, that was all pushed as well.
They did the same thing with 9/11 when I was in school.
I don't think I've ever watched on telly at school like that with the Melbourne uprising.
But Ruhit, no reason to question why men claim to have landed on land in the sky.
Yeah,
people are
no
showing
reason
their
to
ages
question
now. People are showing their ages now with these events.
Can I have a whinge about taboo conspiracy?
What's a win?
Whinge.
Whinge.
Yes, you can go for it. No one.
He's one of your favorite content creators, right? You're a biggest fan.
I'm shouting into the void because I keep he's blocked me on his channel, and I keep emailing him like just basic shit that he's missed. But in the one today, he's shown a observer location, right? And I've replicated the observer location on Google Earth. And if the guy is there, then he's looking at a mountain of dirt, right? I'll show you what I mean. I'll stick this in the chat. All right, so this is a screenshot from Taboo's video. Right. Speed, come on. Come on, internet. There we go. So that's where he says the camera was. Right. And now posting zoomed in from Google Earth. Cool. And now let's drag in Street View. I'll get a look at Street View. And if that's where he was, he's looking at a big wall of dirt. All right. The third one. If that's where he was, that's what he's looking at. This big pile of dirt where there's now wind turbines. Just the lack of precision.
What was he saying that he was meant to be doing?
Well, I'm assuming he was on the top of that mound, which makes him twice as high as he said he was. Not that it matters. The whole thing is that he's going to misidentify the ship. So anyway, that's my whinge, my whine. Is the lack of precision and the lack of verification for what he's actually looking at. I guarantee he's misidentified the ship. Anyway.
Wouldn't honesty come into it?
Yeah. Like, I don't know. If you were honest and I was very politely emailing you that you've misidentified something and showing that you've misidentified it, is it? I don't know.
I'd correct myself in some way.
Yeah, so would I. But he doesn't seem to. Anyway, that's my whinge. Oh, levelist all over it.
You had to help interpret what we're talking about. Jeez.
Yeah.
Wow.
But yeah, I've requested the like marine traffic data for the ship or for the area on that day, and we'll see what it reveals. Oh yeah, what's his name? No Globe. Where'd he go? No Globo Domo. You're the Czech guy. Is that right? You're on the Flat Earth Friday.
Yeah, it's me.
Nice. I was Bruised Ferret on the Flat Earth Friday yesterday. And you
you were.
You're keen for debate.
yeah, you were, he says.
Oh, yeah. I don't know, you sound like you're keen for debate because you were tooting your own horn, as they say.
Honestly, my English is not so great to like do fluent debate about any topic. But what topic do you want to talk about?
7/6 refraction. Leave him alone. Don't do it. Not worth it. Steer clear. I'm just kidding. It's fine.
I think your English is great. Like I've had 2 Czech girlfriends like 20 years ago.
Oh,
you can talk Czech.
No, not anymore. But I had 2 exceptionally hot.
He said that means
Veronica?
you can understand him better. Yeah.
Veronica and Shaka.
Yeah, I think the amount of communication that you guys will have proportional to how much sex we have had with your countrywomen.
Yeah. One is now a Pilates instructor, and the other one was a dancer. So
that's greasing the wheels nicely for you guys to have a nice debate. I think that's super on point.
What was his name?
Har. Flat Earth Math. I took a different approach to the sun.
Dude, you leave our buddy No Globe alone. All right, the dude's holding down all of a country on our behalf.
Yeah, he's a good boy. He didn't do nothing wrong. You leave him alone.
And
Can you unmute for a second, Charles?
What?
Charles, what do you mean the Mount Canningu of ship sightings?